In this session, we've curated a collection of the most mind-expanding theories known to humankind. Each concept will be presented in an accessible way, enhancing your understanding and sparking curiosity. The ideas in this session will gradually become more complex as we dive deeper into the concepts. The holographic principle. Okay, so this one's going to sound completely nuts, but stay with me. Imagine you're standing in a room, right? Books everywhere. Shelves on shelves, stacked with information, like history, science, stories, everything. Now here's the weird part. What if all that info wasn't inside the books, but actually written on the walls of the room? Like the books are just a 3D illusion, but the real stuff is on a flat surface around you. That's basically the holographic principle. Yeah, wild. But some physicists seriously think the entire universe might work that way. That everything we see in 3D, trees, people, the stars, is actually just a super detailed projection of data that's encoded somewhere out on the edge of the universe, like a cosmic hologram. Where'd this idea even come from? Black holes, weirdly enough. Back in the 70s, a couple of geniuses, Bekenstein and Hawking, noticed something off about black holes. You'd think the amount of stuff in a black hole would depend on how big it is, right? Like volume. But nope, it's actually tied to the surface area of the event horizon, that no going back edge. So that got people thinking, maybe what's inside the black hole is somehow described by what's on its surface. Then in the 90s, this guy Susskind was like, hold up, what if that applies not just to black holes, but to literally the whole universe? So he dropped this theory that maybe our reality is just a 3D movie being played on a 2D screen way out in space. Now, I know it sounds like something from a sci-fi movie, but this isn't just some stoner thought experiment. It actually lines up with string theory, which is this big framework physicists use to try and explain, well, everything. In some versions of it, the holographic thing just kind of happens naturally. And if it's true, that means space and time, like the stuff we live in, might not even be the base level of reality. They could be side effects, just layers built on top of deeper information. So does that mean we're not real? Nah, not like that. I mean, a hologram still looks real. You can't walk through it. It's still there. It just means that the realness is coming from something more fundamental. So like your thoughts, your feelings, your breakfast this morning, they still happened. They're just being rendered from a deeper blueprint. Honestly, it might even help explain some of the biggest messes in physics, like why quantum mechanics and general relativity don't really get along. Maybe they're not broken. Maybe we're just missing the bigger picture. Scientists are still working on it. Some signs point toward it, some don't. But the fact that it's even possible, that's what blows my mind. Makes you wonder how much of reality we're just guessing at. Bottom line, we might be living in a 3D illusion, and it still feels completely real. Quantum entanglement. All right, let's talk about something that even made Einstein go, what the hell, quantum entanglement. So here's the short version. Two particles get connected in this special way, entangled. And no matter how far apart they are, what happens to one instantly affects the other. Like instantly, not fast, like literally no delay, even if they're light years away from each other. It's like having two dice that always land on opposite numbers. You roll one and it lands on a 6, the other one, no matter where it is, instantly becomes a 1, even if it's on Mars. Einstein hated this idea. He called it spooky action at a distance. Because it breaks one of the big rules. Nothing should be faster than light. But guess what? We've tested it again and again. And it works. Nature just doesn't care about our rules. Here's the part that really messes with your head. In quantum physics, stuff doesn't really exist in a definite state until you look at it. It's in this hazy in-between zone where it's kind of doing everything at once. A particle could be spinning up and down at the same time. It's only when you check that it chooses a side. Now take two of those particles, entangle them, and separate them. Doesn't matter how far. When you look at one, the other one immediately collapses into the opposite state. It's not like a signal was sent. It's like they were never really separate to begin with. You want an analogy? Think of two sealed envelopes, one with a red card and one with a blue. You and a friend take one each and go to different cities. When you open yours and see red, you know your friend has blue. Simple, right? But in the quantum world, before you open it, the cards aren't red or blue. They're both and neither. It's the act of opening the envelope that decides what color your friend's is too. Like, your choice creates theirs. Yeah, that's how weird it gets. But here's what's cool. We're actually using this stuff now. Quantum computers, which are like the next generation of machines, use entanglement to do wild calculations. And there's quantum encryption too. Basically, unhackable communication. The future's gonna be full of this stuff. But even beyond the tech, there's something kinda poetic about it. It's like the universe is reminding us that everything's connected. Not just in a metaphorical way, but like physically, deeply, weirdly connected. Even when things look far apart, maybe there's still one thing underneath it all. And that's honestly beautiful. But how does this instantaneous connection actually happen? Quantum mechanics doesn't really give us a clear answer, at least not in the way classical physics would like. What we do know is that entangled particles are described by a single wave function, a kind of mathematical object that holds the probabilities for all possible states the particles can be in. And when we measure one of them, that wave function collapses. Not just for one particle, but for both, instantly. It's like flipping a switch, and both lights respond, no matter how far apart they are. But here's the trippy part. There's no signal going from one particle to the other. At least, not in any way we understand. And that's what makes this whole thing so controversial, and honestly, kind of beautiful. Einstein's theory of relativity says that information has a speed limit. Nothing can travel faster than light. So when two particles seem to affect each other instantly, over huge distances, it looks like they're breaking that rule. But quantum mechanics has a different take. It's not that anything's traveling faster than light. It's that the particles were never really separate to begin with. They're part of the same system even if they're on opposite sides of the galaxy. So there's no need to communicate. They're already entangled. And this isn't just theoretical. Entanglement has been tested over and over, especially in what are called Bell test experiments. And every time the results show that no local hidden variables, no secret information hiding in the background can explain the weirdness. Einstein had hoped for a more intuitive explanation. But nature seems to have chosen something stranger, and the implications go way beyond thought experiments. Entanglement is now at the core of some of the most exciting areas of science and tech. Quantum computing, quantum cryptography. These are real developing fields, stuff that could totally reshape how we think about information, security, and even reality itself. So yeah, we still don't know how it works exactly, but we know that it works, and that's enough to keep physicists and dreamers awake at night. Entanglement and quantum technology. Entanglement is used to link qubits, which are kind of like the quantum version of classical bits. Now, classical bits, they can only be a 0 or a 1. But qubits, they can be in a superposition of both at the same time. It's like being in multiple states simultaneously. And when qubits are entangled, something amazing happens. The state of one qubit directly affects the state of another, no matter how far apart they are. This is what makes quantum computers so powerful. Because entanglement lets them perform many calculations at once, they can solve certain problems way faster than classical computers ever could. And then there's quantum cryptography, especially something called quantum key distribution, or QKD. This uses entanglement to securely transmit information. Here's how it works. If anyone tries to spy on the data being sent, that interference will disturb the entangled particles, which means the intrusion becomes detectable immediately. It's like trying to sneak into a room full of lasers. You will trip something. This makes quantum cryptography theoretically unbreakable using normal hacking methods. It offers a level of security we've never seen before. But entanglement isn't just useful, it's also kind of philosophical. It raises deep questions about what reality even is. If particles can stay connected across vast distances, what does that say about space? About time? Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that every measurement creates a new universe, a branching reality, each with its own version of the outcome. Others say, maybe reality is fundamentally non-local, meaning space and time aren't as absolute as we once thought. In the end, quantum entanglement is one of the most mind-expanding ideas in physics. It breaks classical logic. It redefines what we think is possible. And it might just power the future, whether that's through quantum computing, secure communication, or a whole new understanding of the universe. It's a mystery still, but one we're slowly learning to live with. Wheeler's participatory universe. Let's move on to something just as strange, but in a different way. Physicist John Archibald Wheeler had this bold idea that completely changed how we think about the relationship between the observer and the universe. He called it the participatory universe. Now, what does that mean? In short, Wheeler believed that consciousness isn't just watching the universe from the sidelines. It's part of the game. According to him, the act of observing reality isn't passive. It's active. It shapes what we end up seeing. And yeah, it sounds like science fiction, but it's rooted in real quantum weirdness. Let's back up for a second. At the heart of quantum mechanics is this phenomenon called the observer effect. Basically, subatomic particles behave differently when they're being observed. Before you look, they exist in a superposition, like being in multiple places or states at once. But the moment you measure them, that cloud of possibilities collapses. They pick a state. A classic example of this is the double-slit experiment. If you shoot electrons through two slits and don't observe them, they act like waves and create an interference pattern. But if you put a detector there, if you watch, they act like particles. The pattern disappears. Just by observing them, you change how they behave. Wheeler looked at this and said, what if this doesn't just apply to tiny particles, but to the whole universe? And then he took it one step further. What if observation doesn't just affect the present, but the past too? He came up with a thought experiment called the delayed choice experiment. In it, a photon travels toward a barrier with two paths. But whether it behaves like a wave or a particle depends on a choice that's made after it's already passed the barrier. Let that sink in. A decision in the present affects the outcome of something that happened in the past. In classical physics, that should be impossible. But in Wheeler's view, it's exactly what quantum mechanics suggests. Reality, it turns out, may not be fully real until someone looks. Wheeler called this the participatory universe because it means we're not just observers, we're participants. We don't just see the universe, we help create it. Imagine the universe as a jigsaw puzzle, but the pieces only show up when you try to put them together. Until then, they're just possibilities. To describe this, Wheeler used the phrase "it from bit," meaning everything physical, it comes from information, bit. In other words, the universe is made of information. And observation is what turns that information into reality. Kind of like how a video game stays dormant until you press start. The code is there, but nothing happens until you interact with it. Wheeler thought consciousness wasn't just an accident of evolution. It was something the universe needed. He even imagined a feedback loop. The universe produces observers. And those observers, by observing, bring the universe into being. This idea connects with the Anthropic Principle, the thought that the universe must be structured in a way that allows conscious life to exist. Because without us, who would be here to make it real? Wheeler's participatory universe. Wheeler's participatory universe challenges us to rethink what we think we know about reality and about the role we play in it. Instead of a fixed, objective universe that just is, existing totally independently of us, Wheeler suggested something radical. That the universe only fully exists when we interact with it. Observation, in this view, isn't just a way to learn about the universe. It's a creative act, a kind of cosmic handshake. Through the lens of this theory, we're not just sitting in the audience. We're part of the show, not passive spectators, but active participants. We help shape the very fabric of reality solar through the simple but powerful act of observing. In Wheeler's universe, cosmos isn't some distant, uncaring expanse of floating matter and cold energy. It's something far more personal. It's entwined with us. His participatory universe isn't just a theory, it's almost a statement, a deep philosophical one. It says, mind and matter aren't separate. Observation and existence are linked. And maybe, just maybe, we're not just living in the universe. We're helping create it. Information theory of the universe. Now picture this. The universe, not as a physical machine, but as a vast cosmic computer. Every star, every galaxy, even the tiniest particles, they're all part of an enormous flow of data. In this view, what lies underneath reality isn't just matter. It's not just energy. It's information. Bits and pieces of dot eyes or no, 1s and zeros that dictate how everything behaves. This is the information theory of the universe. And it's more than a metaphor. It's a complete shift in how we think about what's real. Imagine the laws of physics as a kind of source code. Space and time? Just architecture for processing information. Even you, your thoughts, your cells, your choices could be described in terms of data. We're used to thinking of computers as being inside the universe. But this flips that around. What if the universe itself is the computer? Not a machine with gears and wires, but a deeper system where the information is the core ingredient. Not mass, not atoms, but bits. And suddenly, everything from black holes to memory, from evolution to consciousness, becomes a question of how information moves, changes, and interacts. It's a mind-bending idea. And if it's true, then maybe understanding the universe means understanding information itself. Information. Theory of the universe. To really grasp the information theory of the universe, you first have to go back to the 1940s, when a guy named Claude Shannon laid the groundwork. Shannon created a way to measure information not based on meaning, but on uncertainty. In simple terms, the more unpredictable something is, the more information it carries. If something can happen in 10 different ways, it holds more info than something with just 2 possibilities. This theory wasn't built for physics, it was for communication systems. But it changed everything. Phones, computers, the internet, they all trace back to Shannon. Now here's the twist. Apply Shannon's logic to the entire universe. And suddenly, reality itself starts to look like a massive system for storing, processing, and transmitting information. Not just particles, not just waves, but data. That's where things get interesting. This leads to the radical idea that the universe might function like a giant computer. A system where galaxies, atoms, and you, yes, you, are part of the program. A cosmic computation running every second, everywhere. Now enter the black hole. Information paradox. According to classical physics, when something falls into a black hole, it disappears behind the event horizon, gone forever. All the information about it, what it was made of, what it looked like, seems to vanish. But quantum physics says, nope, information can't be destroyed, ever. So how do we explain the loss? Some think the information isn't lost, it's just stored on the black hole's surface. Stephen Hawking even proposed that black holes might slowly emit this info through a process called Hawking radiation, which means even the most extreme environments in the universe obey the rules of information. And that led to something even deeper, the holographic principle. This idea says that all the information inside a volume of space can be described by data stored on its outer surface. So yeah, your entire room, everything in it, could, in theory, be described by a thin layer on the walls. 3 dimensions, encoded onto. Wild, right? This idea reshapes how we think about space-time and quantum gravity. It connects the way we store data to the way the universe is. Then there's Seth Lloyd, a physicist who took this one step further. He proposed the universe behaves like a quantum computer, not just storing data, but processing it constantly. Quantum computers use qubits, quantum bits that can be in multiple states at once. That allows them to perform tons of calculations in parallel. So if the universe works this way, then every particle interaction, every law of physics, every moment of time could be part of one giant ongoing calculation. Reality isn't just stuff happening, it's code running. And everything we see, just a visual output of that data. Just like how a photo on your screen is really made of pixels and bits. Matter might be the visible part of hidden information. This flips materialism on its head. It says, matter isn't the base of everything. Information is. That raises deep philosophical questions. If all reality is information, does that mean the universe is some kind of simulation? Are we part of a grand program processing, learning, evolving? Toward what, exactly? Nobody knows. But the theory could help solve major puzzles in physics, like why quantum mechanics and general relativity don't work well together. Information might be the missing link. And what about consciousness? If everything is information, then maybe consciousness is just another layer of information processing. Or maybe it's the part that allows the system to understand itself. In any case, this idea reshapes not just how we look at stars and atoms, but how we look at ourselves. We aren't just observers. We are participants in a living, thinking, evolving computation we call the universe. Digital physics. Now imagine for a second that everything around you, the trees, the planets, your heartbeat, even time itself, isn't continuous. It's digital. This is the heart of digital physics, a theory that says the universe behaves more like a computer simulation than a flowing stream. Not smooth and infinite, but discrete, pixelated at the smallest level. Just like an image on your screen is made of pixels, the universe might be built out of tiny, indivisible chunks. These are things like the Planck length and Planck time, the smallest possible units of space and time. Zoom in far enough, and you stop seeing curves, you see blocks. In this theory, you can't divide space or time forever. There's a bottom layer, a digital grid. The idea is, maybe everything in the universe, particles, forces, light, gravity, is running on code. Just like characters and environments in a video game are generated by underlying software. We might be part of a cosmic program. This isn't just sci-fi either. Back in 1969, computer scientist Konrad Zuse proposed that the universe might literally be a computer. Not metaphorically. Actually, according to Zuse and others who followed him, physical processes, like the orbits of planets or the spin of an electron, might follow algorithmic rules, just like functions in a line of code. Digital physics doesn't deny that we feel reality as smooth and continuous. It just says, that's an illusion created by how information is processed and perceived. Just like motion in a movie is really a series of still frames, reality might be a sequence of discrete events, ticking forward one Planck unit at a time. New? So instead of space-time being a smooth fabric, it could be more like a giant spreadsheet, updated frame by frame, bit by bit. If true, this would mean there are rules, a cosmic logic, and maybe even limits to how much data the universe can store and process. And if we can crack those rules, we might finally answer some of the biggest questions in physics. Why does the universe work the way it does? What are the real building blocks of reality? And could we someday write the code ourselves? Later on, physicist John Archibald Wheeler took digital physics a step further, not just scientifically, but philosophically. He coined the famous phrase, "it from bit." What did he mean? That every physical object, every it, ultimately arises from bits of information. In other words, the building blocks of reality aren't atoms or energy, but information itself, just like in a computer. One of the best metaphors for this comes from something called cellular automata. These are simple mathematical systems. Picture a grid of squares, each one either black or white, and they follow a basic rule like, turn white if two neighbors are black. You run that rule over and over, and suddenly, incredibly complex patterns emerge. Some even look like they're alive. We use cellular automata today in computer simulations to model traffic, fluid dynamics, even biological growth. Physicist Stephen Wolfram ran with this idea. He proposed that the entire universe might be one giant cellular automatona system where incredibly simple rules, applied again and again, could build everything we see. Think of it like this. Just like a game like Minecraft builds complex worlds out of simple blocks, our universe might be constructed from binary rules in or off, 1 or 0. And this brings us to quantum mechanics, where things get even weirder. At the quantum level, particles don't behave deterministically. Instead, they act more like a probabilistic computer system. Qubits, the fundamental units of quantum information, can be 0, 1, or both at the same time. That's superposition. Quantum systems evolve in ways that feel less like physical laws and more like an advanced information process. Take entanglement, for example. Two particles somehow stay connected, no matter how far apart they are. It feels like instant communication, but no signal travels. To some, this looks an awful lot like data transmission on a scale beyond our current tech. So digital physics begins to paint a picture. The universe behaves like a computer. And if that's true, it naturally leads to one of the most mind-bending ideas out there: the simulation hypothesis. Simulation theory. Simulation theory is bold. It suggests that reality, everything we see, hear, feel, might not be real in the traditional sense. Instead, it could be a simulation, not a dream, not an illusion, but a highly advanced digital replica of reality, like a video game, but on a cosmic scale. This isn't just sci-fi speculation. Philosophers, physicists, and technologists have seriously explored this idea. One of the biggest voices behind it is Nick Bostrom, a philosopher from Oxford. Back in 2003, he published a paper titled, "Are You Living in a Computer Simulation?" He laid out what's now called the simulation argument, and it goes like this. There are only 3 possibilities, and at least one of them must be true. 1. Civilizations never reach a level where they can simulate entire realities. 2. If they do reach that level, they choose not to run simulations, maybe for ethical reasons. 3. Or they do run simulations, and if they do, there are probably billions of simulated realities for every one base reality. If that's the case, then statistically speaking, we are probably in one of the simulations. Let's bring this closer to home. Remember Pong? 2 paddles, 1 ball? That was the beginning. Now we've got games like The Sims, Red Dead Redemption, even VR worlds that mimic life in jaw-dropping detail. And that's with today's tech. Imagine what a civilization could do in 1,000 or 1,000,000 years. They could simulate worlds so real that the people inside wouldn't know they're simulated. Us. Now, here's where it gets spooky. Why does the universe follow perfect mathematical rules? And that's with today's tech. Imagine what a civilization could do in 1,000 or 1,000,000 years. They could simulate worlds so real that the people inside wouldn't know they're simulated. Us. Now, here's where it gets spooky. Why does the universe follow perfect mathematical rules? Why is physics so clean, so programmable? In a simulation, you need consistent rules. Gravity, light, energy, they all have to follow strict code. So what if those laws are actually just lines of cosmic software? And then there's quantum mechanics again. In quantum experiments, particles don't settle into a state until someone observes them. They exist in a cloud of possibilities until the moment you check. It's eerily similar to how games render graphics. In open-world games, the system only loads the area you're looking at to save computing power. If reality works like that, observation might literally render our world in real time. So why build a simulation in the first place? Maybe it's for research, maybe to study history, or to simulate different outcomes. Or maybe it's just entertainment, like we run The Sims. Some other intelligence might be running us. The motives are unclear, but the possibility is hard to ignore. If simulation theory is true, then our reality is code. Our memories, our emotions, our laws of nature, all part of the program. And whoever runs the system, they might be watching right now. But even if we are in a simulation, that doesn't make our experiences any less real. Our joy, our pain, our choices, they still matter. Because even if we're made of code, we're conscious code. And that's something powerful. However, there are significant criticisms of simulation theory. One major issue is the assumption that it's even possible to simulate conscious beings. Sure, we've come a long way with AI and virtual environments. But true consciousness, our actual experience of being, is still a deep mystery. Can that really be encoded in computer bits? Or is it something unique to biological systems? Another challenge is proof. If we are inside a simulation, how would we ever know? Any evidence we gather would be part of the simulation itself. And the creators, if they exist, could easily manipulate or erase any clues. But let's just imagine for a moment that we could find proof. What would that mean for humanity? Would it make life feel less meaningful? Knowing that everything is, in some sense, artificial? Or would it just change how we see things, like realizing we're part of a massive cosmic drama? Some thinkers actually see simulation theory as hopeful. Because if we're in a simulation, maybe we can hack it. Maybe we could break some of its rules. Or even achieve something like digital immortality by uploading our consciousness into the system that created us. In the end, simulation theory gives us a radical new lens on the universe. It blends philosophy, physics, and technology, and it challenges our deepest assumptions about what's real. Are we really experiencing the true fabric of reality? Or just a version of it? And if it's all code, who wrote it? Even if we're not in a simulation, the theory forces us to confront the nature of consciousness, and that might be the greatest mystery of all. The many worlds. Interpretation. The many worlds, interpretation, or MWE, is one of the most mind-bending ideas in modern physics. It suggests that every time a quantum event happens, like a photon choosing a path, or a radioactive particle decaying, the universe splits into multiple versions of itself. In each version, a different outcome plays out. So instead of one reality where just one thing happens, MWI says all possibilities happen in separate, parallel worlds. Let's start with the problem it's trying to solve: quantum superposition. Quantum particles, like electrons, can exist in multiple states at once. An electron might be both spin up and spin down at the same time. But here's the weird part. As soon as we measure it, it chooses just one state. Why? Why does it collapse into one reality when we look at it? The traditional explanation, called the Copenhagen interpretation, says that the act of measurement causes the collapse. Just poof, it chooses a state. But that feels kind of arbitrary, doesn't it? It doesn't explain where the other possibilities go. It just ignores them. That's where many worlds steps in. In 1957, physicist Hugh Everett proposed that the collapse never really happens. Instead, the universe just splits. All outcomes happen, just not in the same reality. So if you flip a quantum coin, it lands both heads and tails, but in different versions of the universe. You see heads. Another version of you sees tails. It's like you're standing at a crossroads, but instead of choosing one path, you walk down both in different universes. One of the most famous examples is Schrödinger's cat. A cat is placed in a sealed box, and its fate depends on a random quantum event. Until the box is opened, the cat is both dead and alive. In the Copenhagen view, opening the box chooses the outcome. But in the many worlds, view opening the box just splits reality. In one, the cat lives. In another, it dies. Both outcomes are real, just in separate branches. This idea might sound like science fiction, but it has a kind of elegance. It doesn't need any extra rules about collapse. It treats the observer as part of the same system as everything else. Just one big quantum world, constantly branching. If MWI is true, then there could be billions of versions of you. Some who took different jobs, met different people, made different choices. In other universes, entire galaxies might look different. The laws of physics might even change. But here's the catch. These universes are completely separate from ours. So how could we ever know they exist? That's the main criticism. If you can't test it, can you really call it science? Others argue that it removes the meaning from our choices. If every outcome happens somewhere, do our decisions still matter? Supporters of MWI say absolutely. Your experience is still real. And this model gives us a clean, logical way to understand quantum mechanics without adding mystery on top of mystery. It may not be provable yet, but it shows us how strange and beautiful the universe might truly be. Tegmark's mathematical universe. Hypothesis. Physicist Max Tegmark had a bold idea. He proposed that the universe doesn't just follow mathematical laws. It is mathematics. Everything we see, planets, atoms, emotions, even your fundamentally mathematical structures. Not just described by math, but made of it. Let's unpack that. For centuries, science has used math to describe nature. Newton's laws, Einstein's equations, Schrödinger's wave functions all express the universe through clean, mathematical patterns. And the fit is perfect. Time after time, math predicts things about reality long before we observe them. So Tegmark asked, what if the reason math works so well is because reality is math? Think of it this way. Just as a triangle has three sides by definition, a mathematical structure has its own internal logic. So if the universe is one of these structures, then everything we observe is just part of how that structure unfolds. It's a radical shift in perspective. We're not in a universe governed by math, we're inside math itself. Of course, this idea is still highly debated. Critics argue that math is just a tool, something we invented to describe the world. But if Tegmark is right, then math isn't a tool. It's the substance of reality. This raises wild possibilities. Are there other universes made of different math? Would they have different laws of physics? Could we someday discover or create new realities by simply exploring mathematical space? Tegmark's hypothesis doesn't give us easy answers, but it reframes the question entirely. What is real? What is fundamental? And if the universe is math, then maybe understanding math is the closest we'll ever come to understanding existence itself. But Tegmark doesn't stop at saying that math is useful. He takes it much further. He argues that the universe itself is a mathematical structure. Think of it like this: when you run a computer program, everything on screen, the graphics, the sound, the interactivity, it all comes down to binary code, ones and zeros. The program looks complex, but underneath it's math. Just algorithms, formulas, and digital logic. Tegmark's hypothesis says the universe might work the same way. Everything we experience, stars, trees, thoughts, could all emerge from a deeper layer of math. It's not that the universe follows mathematical rules. It is the rule book. This connects directly to Tegmark's idea of the multiverse, which he divides into 4 levels: each more abstract than the last. Level 1. The cosmological multiverse. This is the most familiar. It comes straight from cosmology. The idea is, space is so vast that there are regions far beyond what we can ever observe. Those regions may look different. Different galaxies, different configurations of matter. But they all follow the same physical laws as our universe. They just started with different initial conditions. It's like rolling the cosmic dice over and over, getting new results every time. Level 2. The inflationary multiverse. In this version, things get more exotic. After the Big Bang, there was a phase called cosmic inflation, an insanely fast expansion of space. In this model, different bubbles of space formed during that time, each one becoming its own universe. And here's the wild part. Each bubble could have different physical laws. In one bubble, gravity might be stronger. In another, atoms might not even exist. We live in one bubble where the conditions just happen to support life. But there could be countless others that are totally alien to us. Level 3. The many worlds. Interpretation, this one comes from quantum mechanics. Every time a quantum event happens, the universe splits. Every possibility branches off into its own timeline. So in one universe, you go left. In another, you go right. In yet another, you don't move at all. All of them happen. You're just experiencing one of the outcomes. The rest, they play out in other parallel worlds. Level 4. The mathematical multiverse. This is the most radical of all. Tegmark says, every possible mathematical structure exists, and each one defines a different universe. So there aren't just universes like ours. There are universes built on totally different math. Laws we can't even imagine. Realities that operate in ways our brains might never understand. In these universes, physics as we know it might not apply. Particles, forces, even space and time might not exist the way they do here. At the heart of all this is a bold question. If the universe is math, what does that mean for existence? Tegmark suggests that everything rocks, animals, star systems, just a collection of mathematical relationships. The shape of a planet, the orbit of a moon, even your heartbeat, it's all math in motion. Our entire universe, he says, could be a solution to a giant cosmic equation, where all the pieces we experience are just part of the output. But this raises a deeper philosophical idea. Why math? Why should this be the foundation of reality? Tegmark leans on mathematical Platonism, the belief that mathematical truths exist independently of us. Like how the number 2 exists, whether or not there are 2 apples in front of you. The same goes for equations. Take x2, y2, 1. That describes a perfect circle. Even if no actual circles exist, the math still holds. Tegmark says that complex mathematical structures, like the ones that define our universe, exist the same way. They don't need a physical manifestation to be real. So if that's true, maybe we're just living in one mathematical reality, among countless others. And if the math is right, maybe even consciousness, emerges from mathematical interactions. Your thoughts, your emotions, your memories, all could be part of a vast abstract pattern. This opens doors to some incredible questions. Could other kinds of consciousness exist in universes with completely different math? Could beings arise who think, feel, and live, but in ways totally beyond human comprehension? Tegmark's idea is daring. It reframes everything we know about reality, not just as something physical, but as something deeply, fundamentally mathematical. If he's right, then we are all part of an equation. A living, breathing, conscious piece of a structure that stretches across an infinite mathematical multiverse. The Anthropic multiverse. Let's turn now to a question that's haunted us for centuries. Why are we here? Why is the universe just right for life? This is where the Anthropic Principle comes in. It says the universe seems perfectly fine-tuned to allow conscious beings like us to exist. Gravity, electromagnetism, particle masses. They all have just the right values. If any of them were slightly off, stars wouldn't form. Planets couldn't exist. Life would be impossible. But what if our universe is just one of many? That brings us to the anthropic multiverse. Imagine standing at the edge of a calm lake, its surface perfectly reflecting the sky. Now imagine that beneath that stillness lies an entire network of hidden lakes, each one different. Some shallow, some deep, some filled with life, others barren, each governed by its own conditions. That's what the multiverse might be. A vast collection of universes, each with its own set of rules. In some, life never had a chance. In others, life might exist in totally different forms. We're in this universe because it happens to support us. We're not here because the universe was made for us. We're here because only this kind of universe allows anyone to ask the question in the first place. This is known as a cosmic selection effect. There could be billions of lifeless universes out there, but we only observe the one we're in because it permits observers. It's like a cosmic lottery, and our ticket just happened to hit the right numbers. This idea isn't just philosophical, it's gaining ground in science too. String theory, quantum mechanics, inflation theory, they all support the possibility of multiple universes with different physical laws. In this view, we are one outcome in a vast sea of possibility, not the center, not the purpose, but a natural consequence of a universe that can happen. The anthropic multiverse doesn't answer all our questions, but it offers a framework. It helps explain the fine-tuning without assuming design or intention. And in doing so, it connects us to something much larger. A cosmic landscape where life, consciousness, and even the laws of nature themselves are just one set of possibilities in an infinite reality. In string theory, for example, there are many different ways in which strings can vibrate, and each unique vibration gives rise to different physical constants and forces. This means that each possible vibrational state corresponds to a different universe, adding even more diversity to the already vast tapestry of the multiverse. But the implications of the anthropic multiverse go way beyond abstract theory. They challenge how we think about reality, about existence, and about our place in all of this. If our universe is just one among countless others, what does that mean for the meaning of life? Is our consciousness just an accident, a spark in a cold, indifferent multiverse? Or could it serve a greater role, a necessary thread in the fabric of something unimaginably vast? These are profound existential questions, and they force us to reconsider the nature of reality itself. As we explore the anthropic multiverse more deeply, we are invited to look not just outward, but inward, to ask what it means to exist in a universe that allows for thought, emotion, curiosity, and life. Through this framework, we can reflect on not just the cosmos, but the very essence of being. A journey begins across infinite possibilities, where each universe is a unique act in the unfolding story of existence. Eternal inflation. Picture blowing up a balloon, but instead of it stopping at a certain size, it keeps expanding forever. Now imagine that as it inflates, tiny bubbles start to form on its surface. Each bubble begins to expand as well, forming new bubbles, which form even more. That's the basic idea behind eternal inflation. It's a model in cosmology that suggests our universe is just one of many born from an endless, self-perpetuating process that creates entire universes like bubbles in an ever-expanding sea. To understand it, let's back up to inflation theory itself. In the early 1980s, physicist Alan Guth proposed inflation as a fix to some problems with the standard Big Bang model. The Big Bang said the universe expanded from a hot, dense point, but didn't explain why space is so uniform and flat across unimaginable distances. Inflation added a twist. It said that just after the Big Bang, a fraction of a second, the universe expanded exponentially. faster than the speed of light. This smoothed out any early lumps or irregularities, explaining why the cosmos looks so even today. But here's where it gets even more interesting. As scientists studied inflation more closely, they realized it doesn't have to end everywhere at the same time. In some parts of space, inflation stops forming what we see as a universe. In other parts, it keeps going. And those regions can spawn more universes, each with their own properties. This process, repeating endlessly, is what we now call eternal inflation. It's like a chain reaction. One universe forms, but inflation keeps going elsewhere. More universes pop into existence, and it never stops. At the heart of eternal inflation is the interplay between quantum mechanics and general relativity. The key player here is something called the inflaton field, a kind of energy field that drives inflation. Due to quantum fluctuations, some areas of this field decay, ending inflation. Others stay stuck, allowing inflation to continue. That's why new universes keep forming in an endless cosmic dance. Each of these bubble universes could have completely different laws of physics. Some may look like ours with stars, planets, and maybe even life. Others might be totally unrecognizable with no atoms, no gravity, or dimensions we can't even imagine. Eternal inflation changes how we see our own universe. Rather than being everything, it's just one bubble in a much bigger sea, one among countless others, maybe even an infinite number. This leads us to the multiverse natural consequence of eternal inflation, and it raises wild possibilities. Could other versions of you exist in another universe? Ones with different outcomes, different laws, different stories? Maybe. If eternal inflation is correct, then such alternate universes aren't just possible, they're inevitable. But can we ever reach them? Probably not. The space between our universe and others is expanding too fast. Faster than light. That makes these bubble universes unreachable, at least with any technology we can imagine. Still, their presence could influence our universe in indirect ways, subtle effects in the cosmic background, or strange patterns in the structure of space. Like any big theory, eternal inflation has its critics. The biggest one? We can't directly observe these other universes. If they're out of reach, how do we prove they exist? And then there's the philosophical side. If there are infinite universes, does that mean everything happens somewhere? Does free will even mean anything in a multiverse where every outcome plays out? These are deep questions, and not all of them have answers. But that's what makes eternal inflation so powerful. It doesn't just explain where we came from, it challenges everything we thought we understood about beginnings, endings, and existence itself. Whether it turns out to be true or not, eternal inflation gives us something rare, a glimpse of the universe as a place where creation is constant, where the cosmos isn't just a story that started once, but an ongoing, infinite unfolding, one bubble at a time. The Big Bounce. The Big Bounce is an alternative to the traditional Big Bang model. According to this theory, the universe didn't begin with a single, one-time event, but has instead been cycling through expansion and contraction for an infinite amount of time. In each cycle, the universe expands from a compressed state, reaches a maximum size, then collapses back in on itself, only to bounce back and begin expanding it again. Instead of a universe that starts from nothing and expands forever, the Big Bounce proposes something different, a universe with no true beginning or end, only transitions between different states of contraction and expansion. To really understand the appeal of this model, we need to take a closer look at the problems with the Big Bang and the concept of a singularity. In the standard Big Bang theory, the universe begins as a singularity, a point of infinite density and temperature, where all known laws of physics break down. This is a problem, because a singularity doesn't give us any tools to meaningfully describe reality. At that moment, our understanding of time, space, and matter just stops working. Physicists have long struggled with this. Why would the universe start from such a state? What caused the singularity? Why did it expand? These are questions the Big Bang leaves unanswered. The Big Bounce offers a solution by avoiding the singularity altogether. In this model, the universe doesn't emerge from nothing. Instead, it comes from the collapse of a previous universe. As that universe contracts, the physics of the cosmos begin to shift. Just before it collapses entirely, some mechanism, like quantum effects or a change in space-time geometry, causes a rebound. The universe bounces back from that collapse and begins to expand again, just like it did after the Big Bang. Each cycle is like a cosmic breath. The universe contracts, reaches maximum compression, and then exhales into a new expansion. Not a one-time event, but an eternal rhythm of the cosmos, stretching back forever. And maybe forward, too. One of the biggest challenges here is explaining what actually causes the bounce. In classical general relativity, when a universe collapses, it collapses into a singularity. But according to proponents of the Big Bounce, quantum gravity might prevent that outcome. One possible framework, loop, quantum gravity, or LQG. LQG suggests that space and time are not smooth and continuous, but are made of tiny, discrete loops. At extremely small scales, space-time becomes quantized, and this prevents the singularity from ever forming. So, as the universe contracts to a near collapse, quantum effects take over. They stop the collapse and trigger a bounce. The fabric of space-time, it turns out, might have a kind of built-in resistance. It can't compress beyond a certain point. When it gets there, it rebounds. But we haven't found direct evidence for the Big Bounce yet. Physicists are searching for clues in the cosmic microwave background, the faint radiation left over from the early universe. If multiple bounces occurred, there could be tiny telltale imprints hidden in that background. Another possible source? Gravitational waves, subtle ripples in space-time. Some researchers believe waves from previous cycles could still be detectable. Of course, this theory has its challenges. It still needs to explain the role of dark energy and why the universe seems to be expanding faster over time. Philosophically, though, the Big Bounce is profound. If the universe is cyclical, it challenges our ideas about beginnings and endings. There's no single moment of creation, no ultimate final act. Existence becomes eternal, an endless dance between collapse and rebirth. For some, this is comforting. For others, it's a little unnerving. If the universe has no starting point, what does that mean for us? What is our place in this vast, timeless rhythm? The Big Bounce is still a speculative theory, but by sidestepping the singularity problem, it gives us a fresh way to think about where we come from and where we might be going. In the end, it paints the universe as a cosmic breath, inhaling and exhaling forever. The ekpyrotic universe. Now, imagine the universe is a vast stage, but instead of a single Big Bang, everything we see was born from a collision. Not of particles, but of massive, multi-dimensional objects known as brains. This is the heart of the ekpyrotic universe, a theory that suggests our cosmos was born from a cosmic collision between brains floating in higher dimensional space. The theory emerged in the late 1990s, built on the ideas of string theory and M theory. These theories suggest that our universe isn't limited to 3 spatial dimensions. Instead, there might be more hidden dimensions we can't directly observe. And within this expanded framework, brains are vast, flat sheets stretching across those extra dimensions. They can move, interact, and sometimes collide. The word ekpyrotic comes from ancient Greek meaning conflagration, or born of fire. It evokes myths where the world is created from a great burning. In this case, the fire is replaced by a collision of cosmic impact that gives rise to everything we know. In standard Big Bang theory, the universe starts from a singularity. Then it expands, cools, and forms galaxies, stars, and life. But the singularity has always been a mystery, a point where physics just fails. The ekpyrotic model offers something different. Two brains, perhaps representing different universes, exist in a higher dimensional space. They slowly move toward each other, building up tension, like tectonic plates before an earthquake. And then they collide. This collision releases energy not from a singular point but across an entire brain. And that energy creates our expanding universe. There's no singularity in this model, no breakdown of the laws of physics. Instead, the universe begins not in a flash from nothing, but from an interaction in something larger than our own universe. The ekpyrotic model ties closely to M-theory. In that framework, brains are just one type of object that can exist in multidimensional space. Some are tiny, others unimaginably large. And our universe might be just one brain among many. So what does this mean? It means that parallel universes might be real, sitting side by side with ours, just in another dimension. It means that the Big Bang might not be the beginning, but just the result of a cosmic cycle, brains moving, colliding, separating, and repeating. And just like the Big Bounce, the ekpyrotic universe challenges our ideas of origin. Instead of a single, uncaused event, it paints reality as part of a larger, more complex cosmic fabric. Whether or not it's true, it opens the door to extraordinary possibilities. A universe shaped not just by what's within, but by what lies beyond. The collision between two of these brains, that's what triggers the birth of our universe. It's a bold rethinking of cosmology. Instead of our universe being the only game in town, this idea suggests it's just one slice of something much larger, a vast multiverse. What we perceive as the beginning of everything might just be the result of interactions in a higher dimensional arena. One of the most compelling parts of the ekpyrotic universe is how it completely avoids the problem of the singularity. In the standard Big Bang theory, that singularity is where our understanding collapses. Infinite density, infinite temperature, infinite curvature. It's where physics breaks down. We simply have no tools to describe what's actually going on there. But the ekpyrotic model takes a different route. Instead of starting with a singularity, it begins with a slow approach, two brains drifting toward each other over trillions of years. And when they finally collide, the universe doesn't explode out of nothing. It emerges from something real, something structured, something that already existed. The beginning is not abrupt or chaotic, but part of a graceful cosmic process. And here's where things get even more fascinating. That collision. It might not be a one-time event. Just like the Big Bounce, the ekpyrotic theory suggests a cyclical universe. After each collision, the universe expands, evolves, stars form, galaxies swirl, life possibly emerges. And then, after eons, the universe begins to contract again. The brains start moving toward each other once more. Eventually, another collision, another universe. A new cycle begins, like a cosmic heartbeat. This cycle could be eternal, no true beginning, no final end. Just rhythm, just motion, just existence, unfolding forever. Now, let's be clear. The ekpyrotic universe and the Big Bounce share some similar beats, but they're fundamentally different in how they work. The Big Bounce plays out within a single space-time framework, one universe expanding and contracting. But the ekpyrotic model? It's operating in higher dimensions. The driving force is not the contraction of our universe, but the movement of brains in a broader, multidimensional space. It's more complex, and more aligned with the deepest ideas in string theory and M-theory. So what does this mean for us? Well, if our universe is just one brain among many, we're part of something far grander than we can imagine. Are there other brains out there? other universes forming in entirely different ways. Are some of them full of life, while others are completely dark and empty? These aren't just science fiction questions anymore. They're the new frontiers of cosmological thought. If creation happens through collisions, then existence isn't a singular miraculous event. It's a repeating pattern, woven into the deepest fabric of reality. In the ekprodtic universe, the cosmos becomes a place of eternal renewal, where every ending is just the start of another beginning, where we're not the first, and probably not the last. White hole cosmology. Now imagine this a mirror image of the Big Bang. A cosmic event so powerful, it hurls matter and energy outward in every direction. Sounds like the Big Bang, right? But what if, instead of creating the universe from scratch, this event was spewing out matter from an already existing reality? This is where the concept of the white hole comes in. A white hole is the theoretical opposite of a black hole. Black holes pull everything in even light can't escape their grip. But a white hole, it does the reverse. Nothing can go in, but matter and energy can come pouring out. White hole cosmology takes this idea and runs with it on a universal scale. What if the Big Bang wasn't a one-off explosion from a singularity, but the outburst of a white hole? A place where time and space unfold outward, not inward. Let's rewind for a moment. Black holes form when massive stars collapse. Their gravity becomes so intense, it punches a hole in space-time and event horizon, beyond which nothing escapes. Everything that crosses it gets pulled toward a singularity. But now, imagine time running backward. A black hole in reverse is a white hole. Instead of pulling things in, it pushes them out. You can't enter it, but it throws out energy and matter from somewhere. According to Einstein's equations, this concept isn't just science fiction. It's a valid solution, mathematically. But while we've seen black holes, or at least the signs of them, white holes remain entirely theoretical. Still, some cosmologists wonder if the Big Bang itself could have been the result of a white hole. What if our universe was born from a place that was already filled with matter and energy and just started expelling it? No singularity, no infinite density, just an eruption from a different kind of space-time region. Let's talk about time. In a black hole, time slows to a crawl at the event horizon. Inside, it may not even exist as we know it. But in a white hole, time flows in the opposite direction, outward, expanding, creating. If that's the case, maybe what we call inflation, that mysterious burst of expansion in the early universe, was actually driven by white hole-like behavior. A place where space-time was being pushed outward, not from nothing, but from something we don't yet understand. Here's the catch. We have no direct evidence of white holes. None. They're still on the chalkboards of physicists and in the dreams of cosmologists. But they're not ruled out. And if they did exist, especially in the early universe, they could explain a few things, like how energy was distributed, how galaxies formed, and maybe, just maybe, what came before the Big Bang. It's a tantalizing idea, not yet proven, maybe never provable, but deeply inspiring. Because if white holes are real, then the universe is more than just what we see. It's a place where reversal, renewal, and time itself might work in ways we've only just begun to imagine. Others have even suggested that white holes could be linked to the mysterious dark matter that permeates the universe. Since dark matter doesn't emit light but does exert gravitational pull, some scientists have played with the idea that white holes might be responsible for these unseen effects. The link between black holes and white holes. Here's another fascinating possibility. Black holes and white holes might actually be connected. In some models, when matter falls into a black hole, it doesn't just vanish into a singularity. Instead, it could be expelled from a white hole, possibly in a different part of the universe, or even in a different universe entirely. It's a concept that sounds like science fiction, and yet it has some serious theoretical backing. Picture a wormhole, a cosmic tunnel connecting two distant points in space-time. Now imagine a black hole on one side and a white hole on the other. Matter enters one end and exits the other. It forms a kind of closed loop, where nothing is truly lost, just rerouted. While this remains speculative, it's a compelling way to link two of the most mysterious forces in the universe. Black holes and white holes, not enemies, but perhaps partners in the cosmic ballet. Conclusion: white holes and the mysteries of the cosmos. White hole cosmology is still just a theory. There's no direct evidence yet. But the idea itself invites us to reimagine the boundaries of time, the structure of space, and the very nature of reality. Whether white holes turn out to be real or simply remain mathematical ghosts, they open a window into possibilities we hadn't thought to explore. As we push deeper into the cosmos, studying gravity, black holes, and space-time, we may one day discover that white holes aren't just speculation, but a missing piece of the cosmic puzzle. And that brings us to one of the boldest ideas in cosmology, the no-boundary proposal. Back in the 1980s, Stephen Hawking and James Hartle proposed a radical theory, one that challenges the idea of a beginning altogether. The no-boundary proposal suggests the universe didn't start from a single, explosive point. It had no sharp origin, no singularity where time and space suddenly sprang into existence. Instead, it had no boundaries at all. To understand this, imagine the traditional Big Bang. A tiny point of infinite density explodes outward, becoming the cosmos we now live in. This point is called a singularity. But here's the problem. Physics completely breaks down at a singularity. There's no way to explain what happened in that first instant or what came before. The no-boundary proposal eliminates this issue by removing the idea of a beginning altogether. Hawking and Hartle described it like this. Imagine the universe like the surface of the Earth round, finite but without an edge. Walk in any direction long enough, and you eventually return to where you started. No cliff, no wall, no end. The universe in this view is like that, only in both space and time. Instead of a clear start, space and time curve into each other gradually, smoothly, without ever reaching a singular point. To explain this, they introduced a mind-bending concept: imaginary time. Now, this doesn't mean fantasy or fiction. Imaginary time is a mathematical construct, just like how we use imaginary numbers in equations. It allows physicists to model the early universe in a way that avoids the singularity altogether. In this imaginary time phase, space and time behave like two dimensions of space. There's no sharp before or after. Instead, everything is smoothed out. The universe becomes finite, but without a beginning or end. This means no need for an initial creation moment, no need for a prime mover or external cause. The universe just is. A self-contained system that unfolds smoothly from quantum fluctuations. Some versions of the no-boundary proposal even open the door to a multiverse where many different universes could bubble into existence from these quantum beginnings, each with its own rules, its own dimensions, its own fate. This theory reshapes our ideas about origin, causality, and what it means for something to begin. No singularity, no sharp edge, just a smooth, curved fabric where time and space are born together with no need for anything outside of them. And that brings us to another deep idea, the block universe. Imagine you're standing on a street. Cars pass by, people move. You experience time as a flow past behind you, present here, a future ahead. But what if time doesn't actually flow at all? What if every moment, past, present, and future, already exists? And always has? That's the idea behind the block universe. According to this view, Time is like space. Just as all locations in space exist, whether you're in them or not, all moments in time exist too. They're just not all experienced at once. Think of it like a movie reel. Every frame is there. Every moment is recorded, start to finish. You only see one frame at a time, but the whole story already exists. In the block universe, our lives are like those frames. You right now, reading this, are a single frame, but the past version of you, still there. The future version, also there, just not accessible to you yet. This model is supported by Einstein's theory of relativity, which shows that time is not absolute. It can stretch, warp, and behave differently depending on gravity and speed. So maybe time isn't a flowing river, but a frozen landscape. And we're just hiking through it, one step at a time. The block universe forces us to rethink everything. Free will, change, causality, even death. Because if the past and future always exist, then perhaps nothing is ever truly gone. Just out of reach. The Big Bang to the distant future is permanently set. The past is still there. The present, just a specific slice of that block. And the future, it's already written, waiting to be experienced. To understand the block universe, we need to explore the idea of space-time, a term that fuses space and time into one four-dimensional reality. Albert Einstein made this idea famous through his revolutionary theory of relativity, which forever changed how we think about time. In Einstein's view, space and time aren't two separate things. They're woven together, forming a kind of cosmic fabric called space-time. Events, anything from the flash of a star to a handshake between friends, occur at specific points in this fabric. Everything, light, planets, even you, moves through it. Now here's something key. Time is relative. That means different observers can experience time differently, depending on their speed or the gravitational pull they're under. Still, in the block universe view, every event, past, present, or future, has a fixed address in space-time. Nothing is left out. Think of it like a film strip. Every frame of a movie exists at once on the reel, but you only see one at a time as it rolls past the projector light. The block universe says time works just like that. All the frames, every moment in history or the far future, already exist. But we only see one, the now. And here's the twist. The passage of time, this idea that moments flow from past to future, might just be an illusion. We experience life like beads on a string, one moment at a time. The past fades. The future waits. But in the block universe, there's no flow. Every moment is static. It exists permanently in its place. So why does it feel like time is moving? That's a question that still puzzles scientists and philosophers alike. One answer? Our brains. The way we process events gives us the sensation of time moving. It might just be a kind of mental trick, a useful survival feature. Like watching trees fly past from a train window. The landscape looks like it's moving, but you're the one in motion. In the same way, time feels like it flows, but from the block universe's perspective, it doesn't. Now here's the million-dollar question. If every moment is already set, do we really have free will? It's a tough one. If the future is already out there, waiting in space-time just like the past, then are your choices truly your own? One way to look at it is this. You feel like you're making choices because you're only aware of this one moment. You can't zoom out and see the whole block. From your viewpoint, your choices still feel real. And maybe that's enough. Another perspective says, yes, you still have free will, just not in the way we usually define it. You're not creating the future. You're unfolding into it. Your choices, your path, they're already built into the fabric of space-time. You're still the author, but the book is already written. This brings us to another strange question. Why does time seem to move forward and not backward? Why can we remember the past, but not the future? That's the arrow of time, and it's tied to something called entropy. Entropy is a measure of disorder. It increases over time. That's why a glass can shatter, but not unshatter. Why heat moves from hot to cold, but not the other way around. In the block universe, entropy still increases, but this change is just another feature of the space-time fabric. The past has lower entropy. The future has higher entropy. But both past and future are equally real. Entropy gives us the illusion of time's direction, but it doesn't mean the future is any less there than the past. The block universe is a radical idea. It tells us that time doesn't pass. It just is. That the future isn't something we create, but something we move through. It might feel unsettling, but there's comfort in it too. Just as every place in space exists, whether we're standing there or not, every moment in time exists, whether we're living it or not. Time dilation and relativity. Time is a curious companion. It marches forward, indifferent to our hopes, our memories, our regrets. But here's the twist. Time doesn't flow the same for everyone. It can stretch, bend, and even pause depending on how fast you're going, or how deep you are in a gravity well. This is time dilation, a real phenomenon first described by Albert Einstein in his theory of relativity. Let's explore it with a story. Imagine two identical twin brothers, Alex and Sam. Alex stays on Earth. Sam? He boards a spaceship, traveling near the speed of light, to a distant star and back. For Sam, the trip feels like just a few years. But when he returns, Alex has aged decades. Time literally moved slower for Sam. That's time dilation in action. Einstein's theory tells us that space and time are part of a single four-dimensional fabric, space-time. Move through it fast enough, and time slows down for you, compared to someone standing still. This isn't just theory. It's something we've tested with incredible precision. Take GPS satellites, for example. They orbit Earth at high speeds, and they're farther from Earth's gravity. Because of their motion and altitude, time ticks slightly differently for them than it does down here. If we didn't account for that, our GPS systems would be off by miles each day. And it's not just speed. Gravity affects time too. The closer you are to something massive like a black hole, the slower time flows. Imagine standing near the edge of a black hole. To you, everything feels normal. But someone watching from far away would see your clock tick ever so slowly. This is gravitational time dilation. And it shows how deeply time is tied to gravity. Let's picture it. A trampoline, with a heavy bowling ball in the center. That's a massive object, like a planet. Now roll a marble near it. The marble spirals in, drawn to the dip in the fabric. That's space-time bent by mass. And near that dip, time itself stretches. So what does all this mean for us? It means time is not a fixed, universal tick. It's personal. It changes depending on where you are and how fast you're moving. It also raises some haunting questions. If time can warp, who's to say we're all experiencing the same universe? When astronauts return from space, they've lived through a slightly different amount of time than we have. They've quite literally stepped into the future. Gravitational waves. Imagine a tranquil pond, its surface smooth as glass, reflecting the clear blue sky above. Now picture a stone dropping into that stillness. Ripples radiate outward, disturbing the calm, one wave at a time. That simple image captures the essence of gravitational waves, ripples in the fabric of space-time, created by the universe's most violent, most energetic events. Just like the stone disturbs water, massive cosmic bodies colliding black holes, exploding stars, disturb the space-time around them, sending waves of energy outward, across the cosmos. But what exactly are gravitational waves? And how do they help us understand the secrets of the universe? The concept was first predicted in 1916 by Albert Einstein as part of his general theory of relativity. Einstein proposed that massive objects warp space-time, and when those objects accelerate, they generate ripples gravitational waves that travel at the speed of light. But for decades, this idea remained purely theoretical. No one could prove it. No technology existed that could catch such delicate waves. That changed on September 14, 2015. The LIGO Observatory finally detected gravitational waves, confirming Einstein's century-old prediction. The source? A titanic collision between two black holes, 1.3 billion light-years away. It was a moment that changed physics forever. We were no longer just seeing the universe. We could now hear it. To understand how this works, imagine space-time as a rubber sheet, stretched tight. Now place a heavy bowling ball in the middle. The sheet curves, bends, under the weight. That's how mass warps space-time. Now imagine the ball moving, or two balls colliding. They create ripples in the sheet, and those ripples, they're gravitational waves. When massive celestial bodies move violently, they send out those ripples. And LIGO? It measures the tiniest changes, shifts smaller than a proton's diameter, in the distance between mirrors. It's like listening to the whisper of the cosmos, from a billion light-years away. Gravitational waves give us a new sense for exploring the universe, a way to observe things that light alone cannot reveal. We can now detect things once thought invisible: black holes merging, neutron stars spiraling into one another, supernovae exploding in the darkness. By analyzing these waves, scientists learn about the mass, the spin, and the distance of these celestial objects. Each wave tells a story, a moment frozen in space-time, rippling out forever. Even more exciting? Gravitational waves might help us understand forward, dark matter and dark energy, the hidden forces that dominate the universe. And some researchers believe that ancient gravitational waves from the Big Bang could still be echoing across the cosmos, waiting to be found. As technology evolves, the future of gravitational wave astronomy is bright. New observatories, like the Einstein Telescope and the Cosmic Explorer, are in development. They'll reach deeper into the universe, detecting even fainter, more distant events. And the science won't stop there. By merging gravitational wave data with electromagnetic signals and neutrino detections, we'll enter the age of multi-messenger astronomy, a more complete way to explore the cosmos. Gravitational waves have opened a new window. We're no longer just spectators, we're listeners. And what we're hearing is a cosmic symphony composed of collisions, births, deaths, and dances of the universe's most powerful players. Each ripple, like the stone in the pond, reminds us that everything is connected. That space and time are alive, shaped by every explosion, every twist of gravity. As we tune in more deeply, we embrace the thrill of discovery and step closer to understanding the profound story of our unfolding universe. Non-Euclidean geometry. Picture stepping into a room. It's perfectly flat. The walls meet at perfect 90-degree angles. Lines are straight, and space feels familiar. This is the world of Euclidean geometry, the kind of space we learn about in school. In this world, parallel lines never meet. Triangles always have angles summing to 180 degrees, and the shortest path is a straight line. But what if space could bend? What if angles curved, and lines refused to stay parallel? Welcome to the strange, beautiful realm of non-Euclidean geometry. First, let's step back. Euclid, an ancient Greek mathematician, laid down the rules of geometry over 2,000 years ago. One of his most famous rules was the parallel postulate. For any line and any point not on that line, there is exactly one parallel line you can draw through that point. This simple rule built our entire understanding of space for centuries. But eventually, mathematicians asked, what if that postulate isn't the only way? In the 19th century, minds like Gauss, Bolyai, and Lobachevsky dared to reimagine geometry. What they discovered was revolutionary. By tweaking the parallel postulate, they uncovered new kinds of geometry, where space was no longer flat but curved. Two major types emerged: hyperbolic and elliptic geometry. Hyperbolic geometry. In hyperbolic space, there are infinite parallel lines, through a single point not on the original line. Imagine a saddle-shaped surface, or the curve of a Pringle chip. Triangles here have angle sums less than 180 degrees, and lines bend away from one another. Space itself seems to stretch. Elliptic geometry. Now imagine the surface of a sphere, like the Earth. In this geometry, no parallel lines exist. Every line eventually intersects another. Here, triangle angles add up to more than 180 degrees. Think of lines of longitude, they meet at the poles, even though they appear parallel at the equator. These new geometries weren't just mathematical curiosities. They became essential to understanding the real universe. Einstein's general theory of relativity. It depends on non-Euclidean geometry to describe how mass curves space. Imagine light bending around a star. That curve follows a geodesic straight path in curved space. What looks bent to us is actually the natural route through warped geometry. In essence, non-Euclidean geometry shattered the illusion that space is always flat and predictable. It revealed that reality itself can bend, not just figuratively, but literally. So next time you picture space, don't imagine a rigid grid. Instead, think of soft curves, shifting angles, and a universe that's far more dynamic than the lines drawn in our textbooks. From the ripples of gravitational waves to the curves of non-Euclidean space, our universe speaks a strange but beautiful language, and we're just beginning to listen. Non-Euclidean geometry in relativity. For centuries, mathematicians believed that Euclidean geometry, flat surfaces, straight lines, and perfect angles was the only way to understand space. But that belief began to shift with the discovery of non-Euclidean geometries. They revealed something extraordinary, that space itself could be curved, and far more complex than we ever imagined. One of the most profound applications of non-Euclidean geometry comes from the world of physics, specifically Einstein's general theory of relativity. This theory completely transformed our understanding of gravity. Instead of treating gravity as a force acting across distance, Einstein showed that it's actually the curvature of space-time, caused by massive objects like stars and planets. Here's an analogy to make it more visual. Imagine a stretched rubber sheet, smooth and taut. Now place a heavy bowling ball in the center. The sheet bends around it, forming a well. If you roll a marble nearby, it spirals toward the bowling ball not because it's being pulled, but because it's following the curve. This simple model reflects how non-Euclidean geometry explains gravity. Mass warps space, and that warping tells other objects how to move. But the influence of non-Euclidean geometry doesn't stop at science. It has inspired artists, two most notably M.C. Escher. His mind-bending drawings use curved spaces and impossible angles to challenge our very perception of reality. Through distorted staircases and infinite loops, Escher visually explored the same ideas that mathematicians use to stretch the boundaries of space itself. And then there's the philosophical impact. If the basic structure of space, something we thought we understood, can be so radically different from our intuition, what else might lie beyond the edge of comprehension? Non-Euclidean geometry forces us to accept that even our deepest assumptions may be wrong. It humbles us and pushes us to explore further. This field of geometry is a testament to the evolving nature of knowledge. It teaches us that there's not just one way to see the world. Space isn't just a flat canvas, it's a dynamic, flexible structure that bends and twists in ways we're still learning to understand. Through the lens of non-Euclidean geometry, we're reminded that the universe is not only vast, but endlessly mysterious and beautiful. And sometimes, the biggest revelations come when we dare to bend the lines. Quantum gravity. Now let's shift from curved space to the deepest mystery in modern physics. Imagine holding a grain of sand. It's tiny, one among billions on a beach. Now zoom in, past the grains, past the atoms, into the subatomic realm where particles like electrons and quarks dance, according to the strange rules of quantum mechanics. But now, zoom out, way out, beyond the planet, beyond the stars, to a universe shaped by gravity, where space-time bends under the weight of massive objects, and black holes stretch physics to its limits. These two realms, the very small and the very large, are described by two of our most successful theories. Quantum mechanics governs particles. General relativity governs gravity and the cosmos. But there's a problem. They don't work together. This is the mystery of quantum gravity, the search for a single framework that can unite the quantum world and the gravitational one. It's like trying to blend two languages that use totally different grammar, syntax, and logic. To see why this is so difficult, let's unpack what each theory tells us. In quantum mechanics, particles don't exist in one place until we look. They live in probabilities, blurry clouds of maybes until measured. Forces are carried by particles, like photons for electromagnetism. Quantum field theory, QFT, takes this further, describing all particles as ripples in invisible fields that stretch across space. It's all very strange, but it works incredibly well. Now enter gravity. In general relativity, gravity isn't a force, it's the shape of space-time itself. Objects follow curved paths, not because they're being pulled, but because mass bends the world around them. Think again of our rubber sheet. No fields, no force carriers, just curves and geometry. But when we try to zoom in on gravity really close, the whole picture breaks down. At scales called the Planck scale, space-time gets bumpy and chaotic, like ocean waves crashing in a storm. It's no longer smooth, it's foamy, and relativity can't handle it. Here's another problem. In quantum field theory, we can deal with infinities. We use a trick called renormalization to cancel them out and get meaningful results. But when we try that with gravity, it doesn't work. The math explodes with infinities we can't clean up. Gravity resists being tamed. So what can we do? Two major ideas have emerged, both trying to bridge this gap. First, string theory. This theory suggests that the tiniest things in the universe aren't particles, but vibrating strings. Different vibrations produce different particles like musical notes on a cosmic violin. String theory also proposes extra dimensions, possibly 11 in total. Most are curled up too small for us to see. It's ambitious. It even predicts a particle called the graviton that could carry the gravitational force. But here's the catch. None of this has been directly proven yet. Then there's loop quantum gravity. This theory takes a more grounded approach. Instead of smooth space-time, it imagines space itself as being made of tiny loops woven together like a cosmic fabric. These loops are incredibly small, but together they form everything. It's like zooming into space-time and seeing a quantum thread. Loop. Quantum gravity avoids the messy infinities and gives us a possible way forward. But again, we don't have experimental proof yet. The stakes are high. A working theory of quantum gravity could help us understand black holes, not just their outside, but what happens inside. It could shed light on the Big Bang and how the universe really began. And maybe, just maybe, it could show us that space and time aren't what we thought they were at all. Maybe they're not continuous. Maybe they're made of something deeper, something quantized, something woven. The journey to quantum gravity is one of the greatest scientific quests of our time. It challenges our deepest assumptions, breaks the boundaries of logic, and dares us to imagine a universe that behaves in ways we're only beginning to grasp. Because at the end of the day, The universe doesn't follow our rules. It follows its own, and we're just trying to listen closely enough to understand them. Quantum loop. Gravity. Just as quantum mechanics revolutionized our understanding of the microscopic world, and general relativity reshaped our view of the cosmos, the development of quantum gravity could be the next great leap in physics. A leap that ties together all of reality, from the tiniest particles to the largest galaxies, into one coherent picture. It's a quest to understand the deep interface between the smallest building blocks of nature and the vast cosmic forces that govern the universe. Quantum loop. Gravity or loop. Quantum gravity, LQG, is one of the most promising ideas in that quest. It tries to merge the two most successful theories in physics, quantum mechanics and general relativity. Quantum mechanics governs the tiny, jittery world of atoms and particles. General relativity explains the massive structure of the universe, galaxies, stars, black holes. The problem, they don't fit together at all. Loop. Quantum gravity offers a bold alternative to other theories like string theory. It's a unique attempt to understand how space-time itself might be made of tiny building blocks broken down into discrete chunks, rather than being smooth and continuous. Let's look at the mismatch first. General relativity tells us that gravity isn't a force, it's the curvature of space-time. Massive objects bend space like weights on a stretched sheet. That model works beautifully for black holes, galaxies, and the expansion of the universe. Quantum mechanics, on the other hand, rules the small stuff. It deals with particles, waves, uncertainty, and probability. Forces like electromagnetism, they're carried by particles, photons, for instance. But when we try to apply quantum mechanics to gravity, things break down. The smooth fabric of space-time that general relativity describes starts to fall apart at unimaginably tiny distances like those near the Planck scale, about 1035 meters across. That's a scale so small, we can't even measure it yet. Enter loop. Quantum gravity. Instead of seeing space as a smooth sheet, LQG imagines it as a network of tiny loops. Think of it like a mesh or a grid, woven together from quantum threads. These loops form what's called a spin network, the scaffolding of space itself. Here's the key idea. Space is quantized. Just like matter and energy come in discrete units, space does too. There's no such thing as infinitely small space. Instead, there are finite, indivisible units. And the same goes for time. Time doesn't flow smoothly. It ticks forward in tiny quantum steps. A radical idea, yes, but one that might reflect how reality truly works at its most fundamental level. In LQG, the structure of space is represented by mathematical graphs, the spin networks. Each edge is a quantum of space, and the nodes where they meet define regions with volume and other properties. Now, as the universe evolves, these spin networks shift and change. Imagine a constantly morphing web of loops, a living, breathing structure of space. When you add time into the mix, this becomes what's called a spin foam, a 4D structure that represents space and time as they evolve together. It's like watching the spin network ripple and churn, foaming with quantum activity. Now here's something truly exciting. Loop. Quantum gravity removes singularities. In general relativity, things like black holes or the Big Bang create mathematical nightmares, infinite density, where physics just stops working. But in LQG, space-time is quantized. It can't collapse into infinity. There's a lower limit, a natural buffer that stops singularities from forming. Instead of a Big Bang, LQG suggests a big bouncy universe that collapses to a minimum size, then bounces back and begins expanding again. Some cosmologists think the universe may go through endless cycles of expansion and contraction. But there's more. In LQG, geometry itself becomes dynamic. It's not a static stage where events play out. It's an actor in the play bending, warping, and responding to the quantum nature of the universe. At the smallest scales, even distance and volume become probabilistic. Objects might not move smoothly anymore. They could jump from one point to another in quantum leaps, just like electrons do in atoms. Loop. Quantum gravity paints a picture of a universe woven from quantum thread space and time stitched together in the smallest imaginable loops. It breaks away from smooth classical geometry and tries to solve the deepest rift in modern physics. And while we're still testing and refining it, LQG opens the door to extraordinary possibilities, new ways of understanding black holes, new ideas about the origin of the universe, and even new hints about how everything ends. If loop quantum gravity is right, then space and time are not just a background, they're the quantum canvas on which the universe paints its story. Poincaré conjecture. Imagine standing on the edge of a vast, endless ocean. You stare out at the horizon, the sea meeting the sky in perfect symmetry. The surface is calm, smooth, reflecting the world above like a mirror. But now, imagine that surface has strange twists, hidden tunnels, and folds that warp your perception. That's the world of topologia, mathematical lens that lets us look at shapes, not by measuring their angles or edges, but by understanding their fundamental structure. Before diving into the Poincaré conjecture, let's take a moment to understand topology. Think of it this way. To a topologist, a donut and a coffee cup are the same shape. Why? Because they both have one hole. The donut's in the middle, the coffee cup's in the handle. You can deform one into the other without tearing or cutting, just stretch and twist. Topology is less about exact shape and more about what's essential. How many holes? How many surfaces? What connects to what? It's about the deep identity of shapes, no matter how they're bent or stretched. Now, enter Henri Poincaré, a French mathematician from the early 20th century. In 1904, he asked a simple-sounding question that would puzzle mathematicians for over a century. If a three-dimensional shape is simply connected, meaning it has no holes, is it always equivalent to a three-dimensional sphere? Poincaré conjecture. In other words, if you have a shape where any loop can be continuously shrunk down to a point, without encountering any obstacles, can that shape always be transformed into a sphere? That's the heart of the Poincaré conjecture. A seemingly straightforward question, but one that opened a Pandora's box of complexity. The conjecture was simple to state, but exceptionally difficult to prove. And that made it a magnet for mathematicians. For decades, it inspired deep research and wild theories, some successful, most not. The Poincaré conjecture became a focal point in the world of mathematics. It wasn't just a puzzle, it became a journey that brought together fields like algebraic topology, differential geometry, and geometric topology, and yet it remained unproven. For nearly a century, it withstood every attempt to crack it open. Along the way, it also revealed something fascinating, the role of dimensions in topology. The conjecture specifically dealt with 3D shapes. But mathematicians began to ask, what happens in higher dimensions? Interestingly, in four-dimensional space, the conjecture doesn't hold. You can have a simply connected 4D shape that still isn't equivalent to a four-sphere. This made the original 3D version even more special and even more elusive. Then, in the early 2000s, everything changed. In 2003, a quiet Russian mathematician named Grigory Perelman published a series of papers online. They claimed to finally prove the Poincaré conjecture. Perelman's proof built on the work of Richard S. Hamilton, who had developed a technique called Ricci-Flower process that lets mathematicians smooth out the shape of a space over time. Perlman took this concept to the next level, using it to show that any simply connected 3D manifold can indeed be deformed into a sphere. He had done it. He had proven Poincaré's 100-year-old idea. But it wasn't smooth sailing. Perlman's proof was so complex, so mathematically advanced, that it took years for other mathematicians to verify. By 2006, the community finally confirmed it. The proof was correct. Perlman was awarded the prestigious Clay Millennium Prize, which came with a $1 million reward for solving one of the 7 greatest unsolved problems in mathematics. But then Perlman declined it. He refused the prize and walked away from the spotlight. He expressed deep frustration with the politics and values of the math world. His choice sent shockwaves through the academic community. But beyond the drama, his proof stands as a landmark achievement. It's not just a win for mathematics. It changes how we understand space itself. It connects the dots between abstract topology and the actual structure of the universe. The implications are massive. The proof influences areas like physics, computer science, and even biological modeling. But maybe most importantly, the journey of the Poincaré conjecture shows us something deeply human. That a simple question, posed in 1904, can travel across generations, inspire minds around the world, and eventually be solved by a single individual working quietly, far from the spotlight. It's a story of curiosity, perseverance, and the beauty of deep thought. The Poincaré conjecture isn't just a theorem. It's a window into the soul of mathematics. Zero-point energy, imagine a vacuum. A space so empty that nothing exists within it. No matter. No particles, not even light. Just emptiness. In classical physics, we'd expect that kind of vacuum to contain no energy whatsoever. But quantum mechanics tells a very different story. Even in that so-called emptiness, there's still energy. A vast, subtle hum beneath the surface. This strange phenomenon is called zero-point energy, and it has fascinated physicists for decades. In simple terms, zero-point energy, ZPE, is the lowest possible energy a quantum system can have. Even when it's at rest, even when all motion has stopped, there's still energy present. In classical physics, a particle can just sit still, motionless, silent, completely empty of energy. But in the quantum world, nope, that stillness doesn't exist. Because of something fundamental called Heisenberg's uncertainty principle. This principle says you can't know both the position and momentum of a particle exactly. If you know one with precision, the other becomes uncertain. That fuzziness applies to energy too. So even in the ground state, the absolute lowest energy condition, there's always a residual hum, a baseline level of activity. That's zero-point energy. You can think of the quantum vacuum like the surface of an ocean. It might look still on top, but underneath, there are constant ripples, tiny waves, endless motion. Even when nothing appears to be happening, energy is there. And we actually have proof of this. One of the best-known demonstrations of zero-point energy in action is the Casimir effect. In 1948, physicist Hendrik Casimir predicted that if you put 2 uncharged metal plates really close together in a vacuum, they'd be pulled toward each other. Why? Because the vacuum energy between the plates is different from the energy outside them. That imbalance creates a measurable force, a real physical push. And when scientists tested it, it worked. We can measure the Casimir effect, which means we can observe zero-point energy at work. Naturally, this has led to some big ideas. If this energy exists everywhere, even in empty space, could we use it? Could we extract it? If we could harness zero-point energy, it would be like tapping into an infinite energy reservoir, a power source that spans the universe. It's the stuff of science fiction fueling starships, advanced cities, and limitless technology. But here's the reality. We're not there. Not even close. While the Casimir effect proves ZP exists, the actual amount of usable energy is incredibly small. And we don't yet have the tools or theories to extract it in any meaningful way. Still, the idea continues to inspire. Some researchers dream of using zero-point energy to power space travel or create new propulsion systems that don't rely on fuel in the traditional sense. Others think it might even offer clues about the dark energy that's causing the universe to expand. One thing's for sure. Zero-point energy reveals that even in nothingness, there's something. A hidden world of vibrations and uncertainty, a cosmic whisper beneath the silence. And in that whisper, perhaps lies a secret to the deepest truths of the universe itself. Others have even proposed that certain unexplained phenomena, like UFO sightings, might actually be the result of advanced civilizations harnessing zero-point energy. But the implications go far beyond speculation. Zero-point energy plays a crucial role in several areas of physics, including cosmology and quantum field theory. For example, ZPE is closely tied to the idea of dark energy, the mysterious force believed to drive the universe's accelerating expansion. Some physicists suggest that dark energy could be a large-scale manifestation of the vacuum's zero-point energy. Even more fascinating, ZPE challenges our very idea of reality itself. It shows us that when we strip away all matter, all motion, down to the most basic, most empty state, there's still something there. An invisible, inexhaustible hum that seems to lie at the heart of existence. That thought alone raises deep philosophical questions. Is the vacuum truly nothing? Or is it the stage for an infinite quantum dance, teeming with unseen forces and energy? Zero-point energy is one of the most mysterious and profound concepts in modern physics. It turns our everyday understanding of emptiness on its head. Because even the vacuum of space is alive with quantum fluctuations, we may still be a long way from harnessing this energy in a meaningful way, but just knowing it exists reshapes how we think about the universe and what it's made of. And even if we never unlock its full potential, zero-point energy will stand as a reminder that even nothing is far more than it seems. The de Broglie-Bohm theory. Now imagine standing at the edge of a vast ocean, watching a boat glide effortlessly across the surface. Its path isn't just powered by its engine, but also influenced by the waves beneath it. Shift your focus now from ocean waves to the quantum realm. In this strange, microscopic world, particles like electrons seem to dance randomly, like leaves in the wind. But what if they aren't so random after all? What if, like the boat, these particles are being guided by an unseen wave? This is the heart of the de Broglie-Bohm theory, also known as the pilot wave theory, an alternative and often overlooked interpretation of quantum mechanics. Let's take a step back. In the standard Copenhagen interpretation, a particle exists in multiple states until it's observed. Only then does its wave function collapse, and the particle's position or outcome becomes known. But this idea has always made some physicists uneasy. It feels odd and unsettling to think that reality isn't definite until we look at it. Enter de Broglie and Bohm. Louis de Broglie proposed the pilot wave idea in 1927. David Bohm revived and expanded it in the 1950s. Their theory says this: particles have real positions and trajectories at all times, even when we're not observing them. But their motion is guided by an invisible pilot wave. Think back to that boat. It's not drifting randomly. The engine moves it forward, but the waves shape its path. In the quantum version, the pilot wave is the ocean and the particle is the boat. Unlike the Copenhagen view, this theory doesn't require the wave function to collapse. There's no magic moment of observation. Reality is always real. Particles exist, move, interact with or without us watching. This is called a hidden variable theory because it assumes certain values, like a particle's exact position, exist but are hidden from us. What's amazing is that this theory still uses the standard tools of quantum mechanics like the Schrödinger equation, but it provides a clearer picture of what's going on beneath the surface. Take the famous double-slit experiment. In the traditional view, particles pass through both slits at once, until observed. But in the de Broglie-Bohm view, the particle goes through one slit, and the pilot wave goes through both. That wave then guides the particle to form the interference pattern we see on the screen. It's elegant, it makes sense, and it avoids the weirdness of a collapsing wave function. So why isn't this theory more widely accepted? One reason is that it reintroduces determinism into the quantum world. Many physicists are cautious about that. Another reason? Non-locality. According to John Bell's theorem, any hidden variable theory must be non-local, meaning that particles can influence each other instantly, no matter how far apart they are. That sounds spooky, but it actually aligns with quantum entanglement, which we know is real. So, the de Broglie-Bohm theory doesn't just explain quantum behavior, it reframes it. It says, particles aren't clouds of probability. They're real things, guided by a deeper reality. It offers a deterministic universe where cause and effect still hold, even at the quantum level. And in doing so, it gives us a powerful new way to understand the strange, beautiful world beneath our everyday reality. Retrocausality. Now picture this. You drop a cup, it shatters. But then, somehow the shards rise, reassemble into the cup and leap back into your hand. Sounds like science fiction, right? Well, that's the kind of logic retrocausality plays with. Retrocausality is the idea that effects can come before causes, that the future can influence the past. It's a wild concept, and it flips everything we think we know about time and causality. Normally, time flows forward. This is what physicists call the arrow of time. Hot coffee cools down. Smoke rises. We remember the past, not the future. Cause always leads to effect. You flip a switch. The light turns on, not the other way around. But quantum mechanics doesn't always care about what feels intuitive. In the quantum world, particles don't have fixed positions until they're measured. They exist in a kind of superposition, a blur of possibilities. And it's here that retrocausality enters the conversation. It says, maybe some quantum events are influenced by things that haven't happened yet. That doesn't mean we can send messages to the past. But it does suggest that some outcomes may depend on future conditions. That, in the quantum realm, time might not be one way. It's a radical idea, but one that's gaining attention as physicists push the boundaries of what we understand about space, time, and causality. Now, let's dive a little deeper into why retrocausality is even considered seriously by physicists. It all comes down to how quantum measurements work. In quantum experiments, like the famous double-slit set-up, a particle like an electron doesn't seem to decide which path to take until it's measured. It behaves like a wave, going through both slits at once, and only after we measure it does it reveal itself as a particle that's gone through one slit or the other. Here's the twist: some interpretations of quantum mechanics suggest that the choice of how we measure the particle can affect how it behaved in the past. Let's say you choose a particular measurement setup. That decision might influence what path the particle took earlier in the experiment. It's not that you changed the past in the Hollywood sense. You didn't go back and stop an event. But rather, the outcome in the present appears to be tied to conditions set in the future. This is the essence of retrocausality. It's subtle, it's strange, and it turns our usual ideas of time upside down. Some interpretations, like the two-state vector formalism, even describe quantum systems as being determined by both past causes and future boundary conditions. In this view, particles are influenced by events on both ends of time. It's like the particle isn't just being pushed from the past, but also being pulled by the future. This doesn't violate causality in the everyday sense. You still can't send a message to your past self, telling you to buy more Bitcoin in 2012. But it does suggest that quantum reality might be bidirectional, with influence flowing both forward and backward in time, at the deepest levels. Now, is this just wild speculation? Not entirely. There are serious physicists and researchers exploring this idea with mathematical models, experiments, and simulations. Still, retrocausality remains a controversial idea. Mainstream physics is cautious because, if true, it would mean that the universe doesn't just evolve from past to future. It's a two-way street. That's a big shift. It would suggest that reality isn't a simple linear thread of moments, but something more like a web, where each moment is linked to what came before and what might come next. At the very least, retrocausality challenges us to think differently about time, about causation, and about how much of the past is really fixed and how much might still be unwritten. It's one of the many ideas in quantum mechanics that reminds us reality might be far stranger than we ever imagined. We begin to question more than just time. We start to ask, where does information come from? Is it possible for knowledge, or even existence itself, to spring from nothing? In The Paradox, the book exists without ever being written. The loop becomes self-sustaining. The author is the reader. The beginning and the end blur into each other. This isn't just a clever twist for science fiction. It poses real problems for physics, information theory, and even logic. One of the most challenging aspects of the bootstrap paradox is how it confronts the principle of causality, the idea that every effect must have a cause. If an object or piece of information exists only because it was brought from the future into the past, and then preserved through time, where did it originate? The loop has no starting point. In physics, this challenges the second law of thermodynamics, which says that systems naturally move toward greater entropy, more disorder. But in a closed time loop like this, the system must somehow preserve order, potentially forever. That raises eyebrows. Still, some theories in theoretical physics don't completely rule out closed time like curves, mathematical pathways through spacetime that loop back on themselves. These could allow for scenarios where the bootstrap paradox becomes more than just a thought experiment. For example, in Einstein's theory of general relativity, there are solutions to the equations that permit time loops under very specific conditions like near rotating black holes or in wormholes. Of course, we haven't found such structures in reality, at least not yet. But the mathematics suggests that time loops might be possible, even if highly improbable. Philosophically, though, the paradox makes us question something deeper, the origin of things. What if some part of our reality, some knowledge, object, or idea, really did originate from a loop in time? What if we're living in a universe where not everything has a clear beginning? That might sound uncomfortable, but it's also strangely beautiful. A kind of cosmic recursion, a universe that feeds back into itself. In many ways, the bootstrap paradox serves as a mirror to our own thoughts. We think, we remember, we dream. But where do those ideas come from? Are we the true origin of our creations? Or are we recycling something deeper, something ancient and timeless? Ultimately, the bootstrap paradox reminds us that time might not be what we think it is. It might not be a straight arrow from past to future, but a spiral, a circle, or even something more complex, folding in on itself in ways that make beginnings and endings indistinguishable. In that sense, this paradox is less a puzzle to be solved and more a doorway into a new way of thinking about reality. A whisper from the universe saying, not everything has to start somewhere. To visualize this concept, imagine sending a message into the pasta signal that arrives before it was even sent. This defies not just physics, but the very logic that underpins our perception of cause and effect. Despite these puzzling implications, tachyons remain a captivating element of theoretical physics. They arise naturally in certain mathematical models, especially in quantum field theory and string theory, where their presence sometimes signals instability in the equations. Rather than being considered actual particles, tachyons are often treated as useful tools, signposts that indicate when a physical theory needs adjustment or refinement. Still, the possibility of particles moving faster than light refuses to be completely ruled out. Physicists have explored a wide range of speculative ideas from wormholes and warp drives to Alcubierre metrics concepts that stretch and bend the very geometry of space-time itself. These models attempt to sidestep cosmic speed limit, not by moving through space faster than light, but by altering the space around an object, compressing it in front and expanding it behind, allowing a form of faster-than-light travel, without violating Einstein's equations directly. Even though these concepts are largely theoretical, they have inspired real scientific investigation. NASA's EagleWorks laboratory, for instance, has conducted research into warp drive mechanics, albeit at an extremely preliminary stage. The appeal of tachyons lies not just in their speed, but in what they represent: the dream of transcending limitations. They symbolize the hope that someday, humanity might overcome the immense distances of space and explore the stars not in centuries or millennia, but in days or hours. But there's a catch. If tachyons do exist, they would bring with them the specter of paradox. Messages from the future, events with no clear cause, timelines that loop in on themselves. These possibilities raise deep questions, not just about physics, but about the very structure of time and information. If the universe allows such particles, what else might it allow? Could tachyons be harnessed to send information backward in time? Would they open the door to communication with other dimensions? Or are they simply theoretical phantoms, forever confined to the pages of mathematics? To date, no experimental evidence for tachyons has been found. Their existence remains purely hypothetical, a curiosity, a whisper from the edge of what we know. But that whisper continues to call. Tachyons challenge the boundaries of reality, daring us to imagine a universe where speed is not the limit, but a doorway. Whether they exist or not, they remind us of the importance of questioning, of pushing past the edges of certainty into the wild unknown. Because in the end, progress is born from curiosity. And the idea of tachyons, like so many strange and beautiful concepts in theoretical physics, serves as a reminder that reality may be far stranger and far more wondrous than we can yet comprehend. Opens up new avenues for understanding the essence of who we are. Could it be that beneath the neurons and synapses, beneath the electrical pulses and chemical signals, there lies a subtler, more elusive mechanism that resonates with the strange, beautiful rules of the quantum world? This idea doesn't just challenge science, it stirs philosophy. If our thoughts, memories, and even identities are shaped by quantum processes, then consciousness itself might not be confined to the brain as a mere organ. It might emerge from the very structure of reality woven into the quantum fabric of the universe. Such a possibility opens the door to questions, once relegated to metaphysics. Is the mind more than matter? Could consciousness extend beyond the body? Are we, in some sense, quantum beings, experiencing a classical world? These questions remain unanswered, but they are no longer beyond the reach of science. As technology advances, tools like quantum sensors, brain imaging, and artificial intelligence may help us probe these mysteries more deeply. And with each discovery, we come a step closer to understanding the profound enigma of the human mind. For now, the brain as a quantum computer remains a hypothesized, an elegant, if speculative, idea. But it is a symbol of our insatiable curiosity or drive to unravel not just the workings of the universe, but the very nature of awareness, perception, and self. Just as quantum particles behave in ways that defy logic, perhaps so too does the mind leaping from idea to idea, connecting thoughts across time and space, dreaming, imagining, creating. In the quiet space between thought and silence, between knowing and not knowing, we may find a glimpse of something greater, a convergence of physics and consciousness that reveals a deeper, more mysterious truth. The universe doesn't just exist out there, it may also exist within us. The simulation hypothesis. Now, let's take an even deeper plunge into the unknown, a theory that flips everything we know on its head. What if reality isn't real? What if everything, our thoughts, our memories, the stars above and the ground beneath, is part of an incredibly advanced simulation? This is the simulation hypothesis, a provocative idea that suggests our universe, our entire existence, could be the creation of an intelligent programmer. At first glance, it might sound like science fiction, but it's a concept that has gained serious traction among physicists, philosophers, and technologists alike. One of its most well-known proponents is philosopher Nick Bostrom, who proposed a compelling argument. If it's possible to simulate conscious beings and entire worlds within computers, then it's statistically more likely that we're living in one of those simulations rather than being the one original biological species. Think about how far we've come. From Pong to hyper-realistic video games. From 8-bit characters to immersive virtual reality, we've already begun crafting digital worlds. If technology continues to advance exponentially, future civilizations could create simulations that are indistinguishable from reality. And if that's possible, what's to say we aren't already inside one? The simulation hypothesis raises some profound questions. Are the laws of physics real, or are they simply code? Is consciousness an emergent property of matter, or of data? And if we are in a simulation, who or what is running it? A higher civilization, an artificial intelligence, or perhaps even ourselves from the future? Some scientists point to strange anomalies in our universe as potential evidence. For example, the behavior of quantum particles, how they seem to decide on a state only when observed, mirrors how computer systems render only what's being processed in real time. Others suggest that the mathematical nature of the universe, its elegant equations, its symmetry, its digital-like properties, hints at an underlying code. But of course, there is no concrete proof. Not yet. The simulation hypothesis is just that, a hypothesis. But it's a powerful one. It invites us to rethink what we take for granted. Our senses, our experiences, even our identities. And beyond the science, it asks something even deeper. If this world is simulated, does that make our lives any less meaningful? Or could it mean that we are part of something extraordinary, a grand experiment, a cosmic narrative, a game with infinite depth? Whether real or simulated, our experiences still matter. Our choices still shape the story. And maybe, just maybe, the purpose isn't to escape the simulation, but to awaken within it. To play our part with curiosity, courage, and wonder. Panpsychism, the idea that consciousness pervades the universe. Imagine looking at a tree, feeling the breeze, or gazing up at the stars. Now, what if all these things, the trees, the air, even those distant stars, had some form of consciousness? This is the core idea behind panpsychism. Bold and ancient view that says consciousness isn't limited to just humans or animals. Instead, it might be a fundamental feature of the universe itself. According to panpsychism, consciousness is present in all things, from the tiniest particles to the largest galaxies in some incredibly basic form. It's a mind-bending perspective that upends the traditional view of consciousness as a rare biological phenomenon found only inside brains. Instead, it suggests that consciousness is woven into the very fabric of reality, just like space, time, and matter. What is panpsychism? The word panpsychism comes from two Greek roots, pan, meaning all, and psyche, meaning soul or mind. The idea is ancient. Pre-Socratic philosophers like Thales once believed that even rivers and stones might possess a kind of soul. But in modern times, this idea is gaining new attention, especially as science wrestles with one of its greatest mysteries, the nature of consciousness. At its heart, panpsychism proposes this. Everything in the universe has a form of consciousness. Not necessarily a rich, human-like awareness, but perhaps a simpler, more primitive kind of experience. In humans, consciousness means thoughts, feelings, memories, and self-awareness. In animals, perhaps a bit less. In plants or particles. Maybe something very basic, a faint, proto-consciousness, like a whisper in the vastness of the cosmos. It's important to clarify. Panpsychism doesn't claim that a rock can think, or that an electron has emotions. Rather, it suggests that even these entities might possess a minimal, elemental form of experience, something so faint and simple. It's nothing like what we know, but it's still something. The hard problem of consciousness. One reason panpsychism has returned to the spotlight is because of what philosophers call the hard problem of consciousness. Coined by David Chalmers, this term describes the challenge of explaining why and how we have subjective experiences at all. Why does a specific brain state result in the feeling of seeing red, or the sensation of pain, or the joy of music? We can measure brain waves. We can track neural activity. But none of that explains why those physical processes are accompanied by the inner light awareness. And this is where panpsychism steps in. Rather than trying to explain how consciousness emerges from non-conscious matter, a task that has puzzled scientists for decades, panpsychism says something radically different. That consciousness was always there. That it's fundamental like mass or charge. And that the rich, layered awareness we feel is just a more complex form of what exists in all things. Panpsychism versus materialism. This idea stands in sharp contrast to the dominant view in science, materialism. Materialism argues that everything, including consciousness, is made from physical matter. It says consciousness only arises when that matter reaches a certain level of complexity, like neurons firing in the human brain. So under materialism, before there were brains, there was no consciousness. Panpsychism flips that assumption. It suggests that even at the beginning of the universe, some form of awareness existed scattered across space and time, embedded in every particle and field. And just as atoms came together to form stars and galaxies, perhaps simple forms of awareness came together to form more complex minds culminating in us. It's a perspective that blurs the line between science and philosophy, between the observable and the mysterious. Panpsychism doesn't prove anything, but it offers a new framework for thinking about the most elusive question of all. What is consciousness? And if it turns out that awareness is not a rare spark in the universe, but rather the light that's been flickering everywhere all along, then maybe, just maybe, we are not alone in our ability to experience the wonder of existence, not just on this planet, but in everything that surrounds us. Panpsychism flips this idea on its head. Instead of viewing consciousness as something that appears only in complex systems, panpsychism suggests that consciousness is already present in the simplest components of the universe. When these components come together in a brain, they don't create consciousness from scratch, they combine their already existing consciousness into something more complex. This idea may sound strange, but some philosophers argue it actually solves several problems that materialism struggles with. One big issue for materialism is this. How does unconscious matter, like atoms or molecules, suddenly give rise to conscious experience? Panpsychism sidesteps this by saying matter was never unconscious to begin with. It's always had a form of proto-consciousness, a tiny spark of awareness that exists in everything. But this leads to a new challenge, called the combination problem. If everything has its own sliver of consciousness, how do those slivers combine to form the unified, rich consciousness that you and I experience? How do the micro-experiences of atoms in your brain, for example, come together to create the seamless awareness of being you? Some critics say panpsychism doesn't really solve the mystery, it just pushes the problem back a level. Instead of explaining how matter becomes conscious, now we have to explain how little consciousnesses merge into one. Philosophers offer different ideas. Some say we may need a new framework altogether to understand consciousness. Others suggest that consciousness might operate under principles we simply haven't discovered yet. In recent years, panpsychism has gained fresh attention, partly because traditional materialism still can't crack the hard problem of consciousness. Neuroscience can track every neuron, every brainwave, but it still doesn't explain why those brainwaves produce the experience of music, emotion, or pain. Philosophers like Galen Strawson and Philip Goff have become vocal advocates for panpsychism. They argue that, while the idea may seem wild at first, it's elegant, consistent, and perhaps the best shot we have at solving this ancient mystery. Some even speculate that quantum mechanics might support panpsychism. In certain interpretations of quantum theory, consciousness plays a role in determining physical outcomes. If that's true, then consciousness may be more fundamental than we thought, woven into the very rules of the universe. In the panpsychist view, the cosmos isn't just a cold machine made of dead matter. It's alive, awake in some form, everywhere. From the tiniest particles to the vastest galaxies, everything may carry its own seed of awareness. It's a bold shift in perspective, but if true, it means we're not isolated observers in a mechanical universe. We're part of an interconnected field of consciousness, a vast web of awareness that binds everything together. And this leads us into an even more radical idea, biocentrism. Biocentrism is a bold theory proposed by Robert Lanza, a biologist known for his work in regenerative medicine. And it flips everything we think we know about the universe. According to biocentrism, life and consciousness aren't just side effects of cosmic evolution. They are central to reality. Consciousness doesn't emerge from the universe. The universe emerges from consciousness. Let's unpack that. In the traditional materialist view, the universe exists out there, independent of whether or not anyone is watching. But biocentrism challenges that assumption. It suggests the universe isn't a fixed backdrop. It's something that comes into being through observation and experience. To understand this, we need to revisit quantum mechanics, specifically the observer effect. In the quantum world, particles like electrons exist in a hazy state of possibility, a superposition, until they are observed. Only when we measure or look at them do they collapse into a definite state. This bizarre effect suggests that observation-conscious observation somehow helps define reality. Biocentrism takes this idea seriously. It proposes that without consciousness, the universe remains undefined, a cloud of probabilities waiting to be brought into focus. And it goes even further. Biocentrism claims that space and time themselves are not absolute objective features of the universe. Instead, they're constructs created by consciousness to help organize experience, like the software framework that runs a virtual reality simulation. In this view, the universe isn't an objective stage on which we act. It's more like a participatory reality, a simulation that activates only when we're there to witness it. This echoes some ideas from Einstein's relativity. According to relativity, time and space are flexible. They stretch and warp, depending on speed and gravity. Biocentrism pushes this further, saying space and time aren't even real until they're perceived. Without consciousness, there is no here or now. There is only potential. Robert Lanza also points to light as a central element in biocentrism. He believes that light isn't just energy. It's fundamental to life and perception. Just as video games remain dormant until the player engages, the universe stays dormant until light meets awareness. In this analogy, biology, not physics, becomes the primary lens through which we understand reality. Biocentrism even reimagines death. If consciousness is what creates reality, then death might not be the end of consciousness. Instead, it could be a transition, a shift in perspective, perhaps even in new realities, generated by the same consciousness that shapes this one. Of course, biocentrism remains controversial. It's a radical rethinking of our place in the universe. But it taps into something deeply human, the sense that we are not passive bystanders, but active creators in the unfolding story of reality. It asks us to imagine a universe, not governed only by laws of matter, but a life responsive and deeply entwined with the very act of being aware. But merely a transition to another state of awareness where new experiences and new universes are created by the mind. Biocentrism is a bold and revolutionary idea that challenges the materialist assumptions that have dominated science for centuries. It suggests that life and consciousness are not passive products of the universe. They are active participants in shaping it. By placing consciousness at the center of the equation, biocentrism offers a new way of understanding the cosmosone in which the mind is not just a latecomer, but a fundamental force that brings reality into being. Whether or not biocentrism holds the key to unlocking the mysteries of existence, it forces us to reconsider the role of life and consciousness in the grand cosmic scheme, opening the door to deeper philosophical and scientific explorations. Emergence Theory. Emergence theory is one of the most fascinating and far-reaching ideas in both science and philosophy. At its heart, it suggests that complex systems and patterns can arise out of the interaction of simple elements in ways that are not easily predictable or reducible to the behavior of those individual parts. It challenges our traditional understanding of how systems work by showing that sometimes the whole is indeed greater than the sum of its parts. Let's begin with a simple analogy to understand this concept. A flock of birds. Individually, each bird follows a relatively simple set of rules. Keep a certain distance, match your neighbor's direction, and avoid collisions. But together, they create a mesmerizing coordinated motion, a swirling, diving, soaring wave that no single bird could orchestrate alone. This emergence in action complex behavior from simple rules without central control. This phenomenon appears all across nature. Ant colonies operate this way. So do ecosystems, economies, and even the human brain. In essence, emergence theory says you can't always understand the system just by studying its parts. Sometimes, something new appears, only when the parts interact in just the right way. Take temperature, for example. At the level of a single atom, it doesn't exist. But once you have billions of atoms in motion, temperature emerges. The same goes for waves in water, traffic patterns, and even life itself. Think about biology. Life is made of non-living parts: proteins, DNA, lipids. Yet, when combined in the right structure, they become something else entirely, something that grows, adapts, evolves. That's emergence. And when it comes to consciousness, emergence may be one of our best explanations. Your brain is made of billions of neurons, each firing or not firing. No single neuron is conscious, but together, somehow they create awareness, emotion, memory, identity. We don't yet understand how, but the whole appears to be far more than the parts. In physics, emergence may even explain space and time. Some scientists suggest that space-time itself might not be fundamental. It could be emergent, arising from a deeper level of reality we haven't yet fully understood. The origin of the universe may also be tied to emergence. The Big Bang describes what happened, but not why the universe is structured the way it is. Some researchers believe the laws of physics and constants of nature may have emerged from even simpler starting conditions. Emergence also raises philosophical questions. If properties can arise unpredictably, does that mean the universe is inherently creative? Could it be more than a rigid machine, and instead, a dynamic, evolving process with built-in novelty? It affects causality too. In classical physics, if you know all the parts, you can predict the outcome. But in emergent systems, small changes in input can lead to dramatic differences, like in chaos theory, where the flutter of a butterfly's wings can cascade into a tornado. In short, emergence theory reshapes how we see complexity. It tells us that new things can arise when simple parts interact, things that can't be explained by looking at the parts alone. From cells to cities, minds to galaxies, emergence may be the creative engine of the cosmos. Morphic resonance. Now we turn to one of the most unconventional ideas in biology, morphic resonance, proposed by Rupert Sheldrake. It's a theory that questions the very foundation of how we think organisms develop and behave. In traditional biology, organisms are shaped by their DNA and environment. Every trait, every instinct, every form coded in genes are influenced by surroundings. But Sheldrake argues something's missing. There are patterns in nature, he says, that can't be fully explained by genetics alone. His answer? Morphic fields. These are invisible, non-physical fields that guide the formation and behavior of living systems. Not like magnetic or gravitational fields, but more like patterns that influence form and memory. According to Sheldrake, when something happens in nature, a crystal forming, a rat solving a maze, a child learning to walk, that action imprints itself onto a morphic field. And over time, this field makes it easier for others to do the same. This is morphic resonance, the idea that organisms draw upon a kind of collective memory of their species. A dog might know how to behave like a dog, not just from DNA or training, but from tapping into this invisible memory field. It's a bold idea, one that treats nature not as a cold machine, but as a living system with memory, habit, and resonance. Critics argue it's too speculative, but Sheldrake points out how little we truly understand about morphogenesis, how form arises in biology. Why do cells know how to organize into organs? Why do species repeat behaviors generation after generation? If morphic fields exist, they could provide an answer, a framework where biology includes both the physical and the non-physical, both the seen and the unseen. Morphic resonance even hints at a deeper interconnection between all life, that habits, instincts, and even thoughts might echo across time and space, not just within individuals, but within the entire web of life. It's a theory that stretches the imagination but invites us to consider, what if memory isn't just stored in brains? What if it lives in the fabric of the world itself? Here's where the concept of resonance comes in. According to Sheldrake, once a particular form or behavior has occurred, it becomes easier for that same form or behavior to happen again in the future. This is because the morphic field for that behavior has been strengthened by previous instances. In essence, the past exerts an influence on the present, not through genetic inheritance or environmental conditions, but through resonance with a field that contains the memory of similar events. This is the process of morphic resonance. A common analogy used to explain morphic resonance is learning. Imagine you're trying to solve a puzzle for the first time. It might take you a long time to figure it out, and you'll likely make mistakes along the way. But once you've solved it, solving it again becomes much easier. Sheldrake extends this analogy to the natural world, suggesting that when one member of a species learns a new behavior or develops a new trait, it becomes easier for other members of that species to do the same even if they're far away and have no direct contact with the original learner. This idea becomes even more fascinating when applied to complex behaviors, the way birds migrate, the way termites build elaborate mounds. According to Morphic Resonance, these behaviors are not just encoded in the DNA, but are also influenced by the collective memory of the species. Each time a bird completes its migration, it strengthens the morphic field for that behavior, making it easier for future generations to follow the same route. Sheldrake has proposed experimental evidence for morphic resonance. One example comes from research on rats learning to navigate mazes. In these studies, rats in different locations were trained to solve the maze. And over time, rats in other locations were able to learn the maze faster despite never having encountered it before. Sheldrake interpreted this as evidence of morphic resonance at work, the collective memory of previous rats, influencing the behavior of rats across space and generations. However, morphic resonance remains highly controversial within the scientific community. Critics argue that there is no rigorous empirical evidence to support the existence of morphic fields or the process of morphic resonance itself. They contend that the phenomena Sheldrake describes can be explained by more conventional means, such as social learning, genetic inheritance, or environmental factors. Many scientists see morphic resonance as a speculative hypothesis that lacks the predictive power and falsifiability required of a scientific theory. Yet, despite the skepticism, Sheldrake's theory continues to attract attention partly because it challenges the reductionist approach of modern science. In a world dominated by materialist explanations, morphic resonance offers a more holistic perspective, one that suggests there may be organizing principles in nature we don't yet fully understand. Principles that transcend the boundaries of space and time. For some, this is a liberating idea, opening the door to new ways of thinking about consciousness, evolution, and the interconnectedness of all living things. One reason morphic resonance is so compelling is that it resonates, pun intended, with intuitive notions of interconnection found in ancient philosophies and spiritual traditions. From the Akashic records in Eastern thought to the collective unconscious in Jungian psychology, the idea that memory lives beyond the individual is not new, but Sheldrake gave it a scientific vocabulary. In the end, whether or not morphic resonance will ever be accepted by mainstream science, it stands as a provocative reminder that our understanding of nature is still far from complete. Sheldrake's work encourages us to stay open to the possibility of unseen forces shaping life and patterns of meaning that lie just beyond our current grasp. The Omega Point. The concept of the Omega Point is a fascinating blend of cosmology, theology, and philosophy, first introduced by Jesuit priest and paleontologist Pierre Teilhard de Chardin. At its core, Omega Point theory suggests that the universe is not simply a physical system, winding down toward entropy and heat death, but is instead moving toward an ultimate, transcendent point of convergence. This convergence, the Omega Point, represents the culmination of all complexity, all consciousness, all order, into a unified, divine state of being. Imagine the universe as a grand narrative. Teilhard believed this narrative had direction. It wasn't random, but purposeful. The evolution of the cosmos, from stars and galaxies to life and human awareness, was, in his view, part of a larger spiritual process. Every leap in complexity, from atoms to molecules, from single cells to thinking minds, was a step forward, a movement toward unity. The final stage of this process, the Omega Point. Think of a sphere expanding outward, yet every point on its surface is being drawn inward toward a central core. The surface is the ever-growing complexity of the universe. The core is the Omega Point, a final moment where everything converges. Matter, mind, meaning. Teilhard, being a Christian mystic, equated the omega point with Christ, the Alpha, and the Omega. But even outside religious contexts, his theory appeals to spiritual and scientific thinkers alike. Why? Because it offers a hopeful vision of the cosmos, one where everything isn't fading into silence, but moving towards divine harmony. From a scientific point of view, the omega point can be reframed as the culmination of evolution, not just biological evolution, but cosmic evolution. A universe that doesn't descend into disorder, but climbs toward greater self-organization and awareness. A place where complexity begets consciousness, and consciousness begets unity. Some have expanded on Teilhard's vision, notably physicist Frank Tipler. Tipler proposed a more technical omega pointone, rooted in general relativity and quantum mechanics. He imagined a future where the universe contracts in a big crunch, and advanced civilizations harness this collapse to create infinite computational power. With this power, they simulate all possible realities, giving rise to eternal life for all conscious beings in a virtual universe. It's a bold and speculative theory, but it echoes Teilhard's dream of consciousness transcending time and death. Of course, not everyone agrees. Many scientists point out that current cosmology suggests the universe is expanding toward heat, death, a lifeless void of maximum entropy, where no energy can do work. This would be the opposite of the omega point, not order, but decay. Teilhard's response, he would say, science explains the mechanism, but not the meaning. Consciousness, he believed, is just as real as gravity or electromagnetism. And while matter may cool and scatter, consciousness can still rise toward unification, toward something more. The omega point challenges us to think bigger, not just about where the universe is going, but about what it means to evolve. Why? To become, to awaken. Is the cosmos a cold machine grinding toward silence? Or is it a living story moving toward something divine, something whole, something conscious? The omega point, therefore, is not merely a physical event, but also a metaphysical one, transcending the limitations of material existence. This brings us to a key philosophical dimension of the omega point, the relationship between matter and consciousness. Teilhard argued that matter and consciousness are not separate, but two aspects of the same reality. As the universe evolves materially, it also evolves spiritually. In other words, the emergence of consciousness is not an accident of biological evolution, but an intrinsic part of the cosmic process. The omega point, then, represents not just the culmination of physical evolution, but also the full realization of consciousness, perhaps even a state where individual consciousnesses merge into a collective or universal awareness. In some ways, the omega point theory resonates with ideas from Eastern philosophies, such as the concept of Brahman in Hinduism, or the idea of nirvana in Buddhism. Both concepts speak of an ultimate transcendent state of being, where the individual self dissolves into a larger, universal whole. While Teilhard's omega point is framed within a Christian context, its echoes are found across spiritual traditions, each imagining the universe moving towards some final, harmonious state. Ultimately, the omega point is a visionary theory that invites us to reconsider the nature of evolution, consciousness, and the universe's ultimate purpose. It offers a counterpoint to the pessimistic view of a universe doomed to decay and extinction, suggesting instead that we are part of a grand, purposeful cosmic journey. Whether one interprets the omega point as scientific possibility, spiritual truth, or poetic metaphor, it challenges us to think of the universe as more than just particles and forces, but as a living, evolving system, moving toward its highest potential. Anthropic Principle. The Anthropic Principle is one of those quiet, philosophical ideas that reshapes how we think about the universe and our place within it. On the surface, it asks a simple question. Why does the universe appear to be so perfectly tuned for life and, in particular, for human life? But dig deeper, and you find yourself facing profound questions about existence, cosmology, and the role of consciousness itself. At its core, the Anthropic Principle is about explaining the apparent fine-tuning of the universe. When we look at the physical constants and laws of nature, like the strength of gravity, the mass of the electron, or the rate of cosmic expansion, we see that they fall within extremely narrow ranges that allow life to exist. If any of these were even slightly different, the universe might be a vastly different place, one where stars, planets, and life as we know it could never form. Let's use a simple analogy. Imagine walking into a room where a giant roulette wheel is spinning. This wheel has millions of tiny slots each, representing a different set of physical laws and constants. As the wheel slows, it lands precisely on one of the rare slots. That allows for life. The question is this just a lucky coincidence? Or is there something deeper going on? There are two major formulations of the Anthropic Principle: the weak Anthropic Principle and the strong Anthropic Principle. The weak Anthropic Principle, or WWAP, is the least controversial. It simply says, we observe a life-permitting universe, because if it didn't permit life, we wouldn't be here to observe it. In other words, the very act of observation biases our perspective. Think of it like this. You're standing on Earth, marveling at how perfectly placed it is in the solar system. Not too hot, not too cold, just right for life. According to WWAP, that's not surprising. Because if Earth weren't in the Goldilocks zone, you wouldn't be here to marvel at it in the first place. This may sound tautological, but it has real implications. It reminds us that our perspective is shaped by the fact that we can observe it all. The strong Anthropic Principle, or SAP, takes things a step further. It suggests that the universe must have the properties that allow life to emerge, that it is not just accidentally fine-tuned for life, but somehow compelled to be that way. In other words, life is not a fluke. It's baked into the structure of the universe itself. This opens the door to more theological or teleological ideas, suggesting that life, and perhaps even consciousness, are not side effects of the cosmos, but central features of it. Some even propose that consciousness is the universe's way of knowing itself. From this perspective, human awareness is not just a lucky outcome, it's a cosmic inevitability. In this sense, the Anthropic Principle doesn't just explain why we exist. It raises the possibility that life and consciousness are the very goals of the universe. Now, one of the most fascinating implications of the Anthropic Principle is its intersection with the multiverse. If we imagine that our universe is just one of a vast number of universes, each with different physical laws and constants, then the fine-tuning of our universe becomes less mysterious. In a multiverse, with infinite variations, some universes would be lifeless, but a few would have just the right conditions for life to emerge. And we find ourselves in one of those few, because that's the only place we could be. Back to the roulette wheel analogy. But this time, imagine not just one wheel, but countless wheels spinning all at once. Each wheel produces a different universe. Some have too much gravity. Some expand too fast. Some never form atoms. But a few land on just the right combination, and in one of those universes, life appears. And eventually, so do we. In this view, there's nothing mystical about fine-tuning. It's just statistics across infinite tries. But not everyone is satisfied with this explanation. Some argue that invoking a multiverse just trades one mystery for another. After all, how do we prove that a multiverse even exists? And even if it does, the strong Anthropic Principle still lingers, suggesting that perhaps there's more to this life-permitting design than random chance. Ultimately, the Anthropic Principle touches a core philosophical debate, the age-old tension between randomness and purpose. Is the universe just a cosmic accident with life emerging in one of many possible rolls of the dice? Or is there a deeper reason, why the universe is the way it is. A reason that points to intention, to structure, perhaps even to consciousness, woven into the fabric of reality itself.